Okay, we're live. Ladies and gentlemen, welcome back to another live stream. Okay, it's been a really long while since I've last live streamed. Hopefully everything is great. Let me share the video or the stream. Please join my Discord server. You can find the link in the description below. Just say discord.codechaco.com and it will bring you to the server. So, okay, let's see what we could do. All right, live. Rust and Vulkan. Once again. Okay. Everyone. And yeah. Let's see the chat. Where's the chat? Huh. Alright, let me just make sure it does actually work. Pop out the chat. There you go. Okay, cool. Let me align this with the camera. Okay, great. Okay. Yeah, that looks about right, I think. Oh boy. All right, so I think we can start already. Hold on a second. I'm just gonna share the stream in my Instagram real quick. Real quick, sorry. Let me know if the quality of the stream is good, by the way, please. There we go. Okay. How do you share this? There we go. Copy link. If you guys have any questions before I start the stream, please let me know. Let's go. Live. Link. There we go. All right, cool. Cool. Alrighty, so I guess let's start already. Let me enable the camera. Here we go, and let's go, man. Very excited for this stream. Let's go. Stream current bitrate is higher than the recommended bitrate. We recommend that you use a stream bitrate of 6,800. Please let me know if the stream is fine, if the quality is good enough. There we go. Seems about right to me. Anyways, let's get going. So we're gonna start a new Rust project. Okay, so I've already done a tutorial using Ash and Rust, though it was incomplete. It did have a lot of bugs, and also I wasn't as good in Vulkan back then. I mean, I'm still not that crazy in Vulkan right now even, but I guess I'm a bit better now. Right, so the second thing is that we're going to be using GitHub Copilot to help us with, you know, boilerplate of Vulkan code, because just one triangle, drawing one triangle using Vulkan and Rust is like more than 1,000 lines of code, you know, so it's just a lot of freaking code, you know. So we're gonna get help from AI to help us write all that code. But anyways, binary application, and what we're gonna call this? Let's go with CodeChaco engine. Rust projects, you better name them like this, you know. And I don't need this guy right here. Okay, like in this kind of manner, you know. So let's just create. Otherwise, you're gonna get an error, or not an error, but like a warning from cargo that the name doesn't match. Here I'm just using a non-commercial use license. You can actually use this IDE. It's my favorite IDEs, JetBrains IDEs. It's called Rust Rover. It's pretty amazing. I really recommend it if you don't have a favorite IDE. I'm just using non-commercial use IDE, like license, sorry, which is free for use as long as, of course, it's non-commercial. But anyways, let's get going. All right, so let's start by adding in some libraries. Well, let's just compile our hello world code for sure, as the culture goes. Hello world, okay, great. Let me make sure I zoom in. Cool. So what kind of libraries are we gonna need? So of course you have multiple choices for libraries when it comes to Vulkan in Rust. You have Ash, Ash Rust, right? You have this binding right here, which is a raw binding, a true raw binding. And though it's unsafe, there's gonna be a lot of unsafe code. It's like we're gonna have like crazy spaghetti of unsafe Rust code, right? And then you also have Volcano. This is a safe wrapper around Vulkan, like around Ash, you know. So in today's stream, we're gonna be using Ash, which is the raw wrapper. Though I did make some videos about Volcano 2 before, like live streams, sorry. And this one is safe, so like you could choose whatever you want. But today we're gonna go with Ash, okay? Sorry, Ash Rust. So we're gonna go with this binding right here, which is pretty cool. It's pretty much the best binding out there for any language, honestly, in my opinion. Like I have a lot of opinionated opinions. Anyways, so the other library that we're going to use is Winit for windowing, like for creating libraries. Otherwise, you're going to be using Win32 API and so on, which is not great. It's not a... Like, I actually done it before, but trust me, you really don't want to do that. Anyways, so windowing handling library in pure Rust. Okay, so this is pure safe Rust. And this is the one that we're going to be using for cross-platform window creation and management in Rust. The other one that you're going to be using is anyhow Rust. So this one we're going to be using it to simplify error handling. So we could use this symbol right here to just return errors, because I don't really care that much about errors. Like I just want to get the error. But anyways, whatever. All right, so other than that, you're also going to be using tracing library. So tracing is basically for logging and debugging. I'm not going to go into a lot of details about this right now. There is also tracing subscriber, because tracing is just like the API, or like just the trait, but you need some implementation. In my case, I'm going to be using tracing subscriber, which is the standard implementation of the tracing library. And a lot of libraries actually uses tracing. So like if you don't enable tracing, then you wouldn't get logs of those libraries. Like for example, WGPU and Winit, these libraries actually uses tracing to log some stuff. Though I think WGPU right now uses log instead of tracing. But anyways, though there's also another library called log though, but log is not async friendly, I think. And it's not as feature rich, as robust as tracing. So yeah. All right, let's keep going. I think what else? We may use GPU allocator for later on to help us allocate buffers and images, you know, like in an efficient manner. So memory allocator for GPU memory in Vulkan DirectX 12. And by the way, for this one, you could use it like for DX12, like DirectX 12, and what is it? Vulkan, yeah. We may use this, we may not use it. I don't know. I'm not sure. I did have some issues with it recently. I used it, but anyways, the other thing that we're gonna use is maybe palette Rust library just for colors, you know, just to have some standard colors, pretty much color crap, right? Color types and color conversions, right? The other library that we're gonna have is, let's see, we may use Tokyo in the future for async and parallel code, possibly, not sure yet. We may use it, not sure yet. So the other one is, of course, if you want images later on, we could use the image crate. And since this is gonna be like maybe an engine, I'm not sure, but we're gonna focus on the renderer using Vulkan. So this is can like load and decode images and so on. The other library that we may use is Rapier 3D. If you want physics later on, Rapier Physics Engine is pretty much the best physics engine in my opinion. You also have parallelism and SIMD, and also cross-platform determinism. This is very important for, like, let's say scientific simulations, to have accurate simulations, and also what is it called? Also networking. So like to make sure, like, let's say you have two simulations on different clients. So like client-sided simulation, physics simulations. You can make sure that like you just put them in an initial state, and cross-platform determinism will make sure that you have the same simulation going on. Otherwise, if you don't have cross-platform determinism, what's going to happen is that because of precision errors in the floating point math operations, what's going to happen is that the simulations will diverge. Anyways, whatever. So Rapier actually uses an algebra, which is a math library, linear algebra library, right? And this is the one that we're gonna use even in Vulkan, in graphics, like the renderer, right? This one is a bit hard to deal with, honestly, but I feel like it's worth it. It's have some amazing stuff. It's just a little bit complex to deal with. And by the way, this guy right here, like this library and the Rapier physics engine, is made by the same entity, Dimforge, right? So, and they're actually dog food in their linear algebra library for their physics engine, right? Or physics library, whatever. So I think that's pretty much it for the libraries. So yeah, let's just keep going. All right, let's start. So cargo add, right? We're gonna add tracing. We're gonna add tracing dash subscriber. Is it tracing dash subscriber? Hold on. Tracing dash subscriber, I think. No, it's there's no standard for this symbol right here for library names. But anyways, cargo add tracing subscriber, and also winit ash. We're also gonna need ash window. This would help us like enroll window handle. This basically will help us create the window without having to use an API. Like, whoa, camera channel, hey, welcome to the live stream. Okay, so by the way, is the live stream quality good? Let me know, please. All right, so ash window, this, as I said, would help us to create a window without having to go crazy with which OS and so on. So like it would help us bridge between winit and ash. I mean, you could actually use any other library, window and library, that implements the raw window handle. But anyways, so what's this called again? Ash dash window, right? Looks and sounds good to me. Great, perfect, thanks. Ash dash window. All right, so what else we gonna need? We're gonna need an algebra for mathematics later on. And what else? Hello, room reveal. I just changed the camera angle pretty much. Okay, so I think that's all we need for now, maybe. Yeah, let's go. All right, there we go. So right now, as you can see, we added these libraries. Great, perfect. Yeah, we're also gonna need bytemuck, by the way. So cargo add bytemuck. Well, bytemuck. Dash features derived, so it can give us a proc macro that we're gonna use later on. And bytemuck basically helps us to get like some values and transform them into, how can I say, transformed, like for example, let's say you have a slice of U32s and you want to transform it into a slice of bytes, like not really transform it, but reinterpret it, right, as a slice of bytes. Then you could use bytemuck to help you do that safely. That's basically what bytemuck helps us with. And I'll show you how, like what we're going to use it for later on. Okay, so other than that, I think we're good to go. Yeah. Okay, let's just go ahead and do this. All right, so I'm not sure yet about the structure, but we're gonna see how it goes. Okay, cool. So let's create a directory. So Winit, by the way, have changed a lot from the other tutorials. It's like it just basically made a lot of tutorials outdated at this point. But today I'll show you how you could actually use it. All right, so directory. We're gonna need a directory for an app, right? So app, and then we're gonna create a, well, not a regular file, we're gonna create a Rust file. We're gonna call this app, well, actually not app, we're gonna call this mod.rs because we're using the folder. And when you use the folder, you have to use mod.rs. So there you go, and we're gonna have a struct app. So I'm gonna have a hierarchy of stuff, basically, but anyways. So struct app, and we're going to implement app handler. So this is inside of Winit. And let me attach first this guy to this. So there you go. Just add mod app here. Cool. So implement application handler. So this is a trait, a new trait in Winit in the latest versions of Winit. So you just implement it for app. I'm going to remove this crap. And let's just implement some members. So this is all the members that you can implement in this trait, like, and these ones are the required, I think, the resumed event and the window event, right? So, and you have also these ones, new events, user event, device event, about to wait, suspended, exiting, etc., etc. Anyways, let's just add these first for now. Okay, so resumed. So they did it like this because in some platforms, you can't make the window until you get a resumed event. Like for example, in Android, you can't make a surface or maybe even a window if you didn't get the app cycle event of resumed, right? And there's also paused, which then you have to actually destroy the renderers and redo it again. I'm not sure if I have to also remake the window, but we'll see. Anyways, for now, resumed is here where we can actually start creating windows. And here we're going to get, of course, the events of the windows. Cool. We're also going to have another directory inside of app called engine. Okay, so you could like structure your project however you want, but this is what looks good to me for now. So mod rs, there you go. Add, I'm also getting like using GitHub, you know, to keep up with the commits. Anyways, so struct engine. What will the result be? Triangle. Well, that's gonna be our first target, which is a triangle, but then hopefully we could like try to make something crazier, right? But first thing would be a triangle, of course, as always. But the thing is, when it comes to graphics APIs, especially Vulkan, once you have a triangle, it's a little bit easier. Well, I mean, it's a little bit easier to actually make more triangles. That's what I mean. And if you can make more triangles, you can make anything else, like, because all geometry is just triangles. Though there is the complexity of buffers and all that other crap. But anyways, whatever. Struct engine. So public struct engine and public struct app too. Cool. All right. So what we're gonna have, and so So I have it this way. We're gonna have engine here, and it's gonna be an option, right? So option of engine. Import. We're gonna import that from the crate, and here in resumed, we're gonna actually say engine self.engine is equal to some engine new, and then we're gonna give it the event loop. So this app right here is basically like an abstraction for me over Winit, so I can do some cool stuff with it basically. And in fact, this would give an error, like a result basically. And I'm just gonna unwrap it here or do whichever I want with it later on. Okay, great. Let's actually create this function here, engine new. There you go. So here we're gonna get the event loop, pretty much. And we could do whatever we want with it. Here we're gonna say result of engine or self. Self basically is engine, right? Okay, self. And we're gonna use anyhow result. So basically the regular standard result, what's happening there is that you need to give it the error type too. But the anyhow result, you only need to give it the you know, the actual OK type. Otherwise, it can accept any other error basically, which is convenient, at least for binaries. Though if you're making a library, you probably want some more structural errors, like error handling. So you're probably gonna use some crate like error or something like that. Anyways. Okay, cool. So what are we gonna do now? And finally, we're gonna have one last module, right? Which is gonna be the renderer, right? So render, and we're gonna have mode.rs here again. There you go. We're gonna have public render, and this is where our stuff will go, pretty much. Oh. Something is weird here. Oh, public struct render, there you go. And yeah, by the way, I almost forgot. If you're using the same IDE as me, please make sure to go to cargo check and run external linter on the fly, because the regular, like the default one, is so trash. And that's the first thing. The second thing, I like to use Rust FMT instead of the built-in formatter. And then also format actions. Save actions, or actions on save. Here we go. You're gonna reformat the code automatically on save, optimize imports, rearrange code, run code cleanup. Apply, okay, perfect. All right, great. So in the engine, we're gonna have renders. So I'm not sure if I really wanna support multiple windows, but I think we're just gonna go with it. Why not? Hash map, so it's gonna be a hash map of window ID from Winit with window, though not any window, arc window. So shared ownership, so it doesn't have problems with the borrow checker, and also so we can satisfy a condition that I'm going to show you later on. Walaikum salam, Woji Kiran, welcome to the live stream. Also recommend using Clippy over cargo check. How can I change that? Like, is there a way to actually change this here? Oh, there you go. Cool. I never tried that, honestly. Thanks. Let's see how it goes. Okay. So here, basically, for every window, you're going to have an associated render, right? So that's basically the case here. And of course, we're going to have windows. And windows would basically be, well, a hash map of window ID, comma, arc window, pretty much. There you go. Cool. So hopefully, if we can, we're going to support multiple windows. And then, of course, we're going to have a main window or primary window. Let's go with that. Option window ID, pretty much. Cool. Cool. I really struggle with structuring my projects, honestly. But hopefully this time I don't F it up again. Anyways. anyways, I either overdo it or underdo it. That's always my case. But anyways, all right. So what we're gonna do now? Yeah, let's start doing our stuff. Okay, so let's start by a primary window here. So primary window, you're gonna say event loop.create window, and it takes one argument, which is window attributes. This is the struct that you could basically customize your window with. There you go. Though in my case, I'm just gonna say window attributes default. I don't care. Though instead of that, you could also just say default, which is more generic, right? So that's great. Primary window, cool. Now after that, primary window ID is basically primary window. Well, let's call this actually primary window ID to reflect more on what the heck is going on there. Though why it's an option, weird, that's strange. By the way, why I actually abstracted the engine over the app is because I don't want to every time, like if I did that, I would have renders is an option of hash map window ID, blah, blah, blah. Windows is an option and primary window ID is an option too. Robert, welcome back to the live stream, and Loop Preliminary, welcome to the live stream. How is it going, Robert? Theo Paris and whoa, GG Gearing. It's been a long time. So anyways, so as I said, so basically instead of having an option for every single field in my engine, I'm just gonna have option engine, right? So that's why I did that. Okay, so but found anyhow result. Oh, sorry, in wrap here, there you go. Cool. The other thing is the fact that here, since this iterate signature is actually controlled by winit, I can't change it, right? And I like to actually like propagate up my errors up the stack of function calls using this thing here. So, but if I actually did my logic here, I can't do that because I can't say that this should return a result. But here, since this is my own struct that I have full control over, I can actually say result. And here I could do whichever I want with the errors that are propagated up the systems, right? In my case, I'm just in-wrapping it for now. So basically, if there's an error, just crash here, basically. Anyways, let's get going. So we have primary window ID now. Cool. And what's next? We're gonna have a renderer, so it's a hash map. And then Windows, it's also in a hash map. And we're gonna say, well, the primary window should be in an arc already, because it shouldn't be owned just by the engine, but also by the renderers. Because if somehow the Windows gets destroyed before the renderer surfaces, we're gonna have a problem, right? So that's gonna be a problem, right? Okay, cool. Now hash map, I think I could say from primary window ID. So you give it an array of tuples, right? Where the key and the value. There you go, renders, that's the renders, and the windows from primary window ID, primary window. Perfect. And that's basically, oh, what I'm doing, hold on. Oh, sorry. Not arc window, but renderer. I may decide to make the renders also an arc, I'm not sure, but well, whatever. Let's just say renderer here, actually. And of course, we're gonna need to create a renderer for a primary window, first of all. So primary render, or actually, no, let's just loop through all the windows and make for them renders, right? So for window in Windows, we're gonna create a new render basically. Let's create this function here. I hate that JetBrains IDE does that for me, but anyways, whatever. So here we're gonna get an arc window. Well, it's gonna be an arc window. It's gonna be a new arc because we like the render should share the ownership of the window. Anyways, and here it's gonna be a result of self, pretty much. And again, we're gonna use anyhow result. Cool. Okay, self. A lot of boilerplate because we're just starting up. But yeah. So window. Iter. So let's clone this window. So we're not cloning the window itself here. We're cloning the arc, right? So we could short ownership. We could give it a. It's kind of like, you can think about arc is like a key, you know. So like if you have one house, you could share it by giving out 2 keys, right? 2 handles, 2 keys for everyone who owns the house, you know. So that's basically what happens when you clone. It's kind of like you don't clone the house itself, but you clone the key, right? So as long as there is multiple keys or like multiple owners, as long as there is an owner, then the house could live on, right? But if there is no owners anymore, then we can actually destroy the house because it's useless at that point, right? No one uses the house, or no one owns the house actually. Anyways, renders hash map from. All right, that looks about right, I think. Well, no. Sorry, let's say let renders is equal to windows.map. Can I say that? Iter.map id window, and then we're going to create a new renderer. And we're going to store in the ID and the render. And we're going to collect into a hash map. Can I do that? Wrong number of expected at least 2 found 1. Oh yeah, my bad. So like that, okay. So here I'm basically telling Rust to figure out the type itself. The only thing that I wanted to actually give it the type for is the container that I want to collect this data into, because it could be a hash map or it could be a vector. Rust doesn't know, but Rust does know what like the types of the keys and the values in this case from here, right? So as you can see, I already determined that it's window ID for the key and render there basically. Let's add the missing fields, and for whatever reason, the Windows doesn't like it. Why? Let's see. Hash map, arc window, but found. Expected hash map window ID, arc window, but found hash map window ID, arc winit window. What the heck is the difference there? Oh, my bad. Well, the IDE, instead of using winit window, uses ashvk window. So this is some error that trips me a lot. So just be careful with that if you're using the IDE to import your stuff like I'm doing here. Okay. If you're using Vim, you gotta figure out what to import, which is gonna be a hell of a ride. But anyways, so that's basically it. We're taking the windows and we're mapping them into renders. We're creating a new render for every single window we have. Cool. So that's the engine. Now let's, I think, start with implementing the render already, yeah? And by the way, beforehand, in the main function here, well, we gotta create our app, right? And we gotta also create our event loop and so on. But first of all, the first thing that we wanna do is to initialize the tracing subscriber so we can actually get logs from libraries and also our own logs. And then we have to create the app. Now, since this app, I'm making it an option because I want to be able to derive default, right? And so it would give us none here for the engine as a start value. And so we're going to say let app is equal to app. As you can see, like the AI, the GitHub copilot is, you know, sometimes it is, sometimes it misses. Though it does get better with how much things you're doing, especially if you're doing something that is common. But yeah. Also, another thing that I want to mention is that I'm going to be using like the latest Vulkan version. I'm also going to be using some modern extensions. I'm going to be using what is it called? Dynamic rendering, so we don't have those crazy frame buffers and render passes. Anyways, so here right now we also need the event loop, right? So let event loop is equal to event loop new. I'm gonna import that, and I'm gonna unwrap this guy, or I could also here say dash result, just for the sake of consistency, pretty much. And we're gonna use anyhow result. Well, what I'm doing. There you go. Use anyhow result, and here right now I could actually do this. Cool. And app dot run, whoa, sorry, event loop dot run app. So this is how you use the newer version of Winit, pretty much. I had to figure it out myself, and of course through the documentation. There's also the examples. You could check out the examples of Winit library in their GitHub repo. But yeah, here you should give it a mutable app. Yeah, there you go. Okay, I make app mutable, so we could borrow immutably. And there's also some platform specific stuff that you may want to read here. So like iOS will never return to the caller, and so value is not passed to this function will not be dropped before the process exits, blah blah blah, whichever. Anyways, so that's basically it. Also, I'm not really gonna care much about compatibility with other platforms, at least for now. So if you're using something other than Windows, I'm probably not gonna really bother too much with it, though I may give you a note that you may need something more to support this platform. Though hopefully later on I could go back to the code, and if anything that needs, you know, cross-platform stuff, we can fix it. Anyways, all right, so great. I think we could already right now run the code. If there was no errors, I'm crazy. Writing all that code and no errors, that would be crazy. Alrighty, so it's compiling all the libraries that we have added. By the way, if there's any questions, please let me know. And there you go. We have our Winit window, our primary window. Though when you try to close it, nothing happens. So of course we gotta handle that too. So here in our app here, we're gonna say self.engine. Well, if let's some engine, self.engine as mutable. So if there is an engine currently, and by the way, the other thing also, we could implement paused, like, where is it? How do I do that? Whoops. I think here, yeah, generate. Okay, there you go. Implement methods. I'm gonna implement, for example, suspended. Okay. So when suspended, we want to destroy the engine. So we're gonna destroy everything. So yeah. This is important for Android, for example. But anyways, here let's actually create this window event function. Oops. Engine.window event, event loop, window ID, event. All right. So let's go to engine here and pubfn window event. There you go. Mutable self, event loop, active event loop, great, window ID, event. Just say this. We're gonna import this. And here what the AI is trying to do, let some render equals self.render is mutable. No need. Just say, right now at least, match event and window event close requested. So when we get the close requested event, meaning that, you know, some window got its X button clicked, right? We're gonna check if it's the main window, the primary window. If it is, then we want to quit the whole application, right? We're gonna exit the whole application. Otherwise, we just want to remove the window in its renderer. So that's basically it. External, I seem to be trying to use match for an equality check. Consider using what? Oh, I see what it's talking about. Basically, it's basically telling me that because I have one arm in this match, I don't really need a match. But though I'm gonna need a match. But okay, fine. For now, we don't need it. Yeah, true. But yeah. Okay, there you go. Let me show you how you could create a new window too. So how are we gonna do that? So like, let's say, for example, upfn create window. So of course you're gonna need to give me the event loop apparently. And somehow, I'm not sure how I'm gonna do that. Interesting. So we're gonna create a new window. Actually, we could use it here, right? So instead of this crap right here, we could actually use our function here. Cool. So let window is equal arc new event loop create window. Well, of course, the window attributes here of the window. So attributes. There you go. So you're gonna give me the event loop, the attributes, and then what? Well, if everything works well, then I'm gonna give you a window ID. Otherwise, an error. And so right now, instead of in wrap, I could actually replace it with that and replace it with that, right? So let window ID, window option V, window ID. Well, we could just, no, we do need the window ID, yeah? Then render new, self.windows.get, window ID, and wrap, clone. No, why do this? The only problem with the AI is that every time it generates something, you have to actually check to make sure that it's doing what you want to do. Right? I mean, this is valid, but I think it would be better if we just say window directly dot clone actually, instead of doing a lookup again, I think. But the value got moved here, so I actually have to clone it here, though I don't need to clone it here because we're not going to need it anymore. We could just basically move it or consume it, right? So after this, I can't reuse the window here because it's got moved here. Though here, I don't want it moved because I want the window to use it here. So I cloned the arc. I cloned the key to the window, right? So the handle. Okay, cool. Expected results window, but found that. Okay, cool. Okay, window ID. So if everything went well, it's going to return okay with the window ID. Great. And now we can actually use our function here, create window. So actually no, we can't use it because we don't have self, right? We don't have self yet constructed, which sucks. Yeah, so we can't use it here. Okay, cool, it's fine, whatever. But basically, let's say we want to create a new window. We can just say, well, let's first make sure that we have an engine, because that's an option. And then you could basically say engine.create window. Like you could say that this is, let's say, a secondary window is equal to engine.create window, event loop, default. Or otherwise, we could say window attributes, default with, let's say with title, for example. And let's give it a title here. So this is our secondary window. Okay. And you could go crazy with that. Anyways, let's try this and see. So this would create both the window and the corresponding renderer. So as you can see, I have a secondary window now and our primary window. And if I try to delete the secondary window, it's just gonna basically delete the window itself only. But if I actually delete, like close the primary window, the whole application would close. Let me show you. So there you go. So both of them goes off. There you go, pretty cool. So now we have done some setup, and right now I think we can start Vulkan stuff, the crazy stuff, right? So anyways, let's go. How are we gonna do this? No clue. All right, so okay, so of course, as always, we start by, I'm gonna create another class or module called context. Okay, and for a good reason, because there's some instances that you do need to pass out a lot, and if you just pass every object by itself, you're gonna have like a lot of, what can I say, you're gonna have a lot of arguments, right, for the functions to create anything. Like, let's say if you want to create a buffer, you know, and like fill it with data and so on, you're gonna pass in the instance, you're gonna pass in the instance object, the device object, the queue objects, and so on. So like a lot of all these objects. So instead of doing that, we could just create one struct that contains all of these main characters, right? The main characters of Vulkan, right? Anyways, so how are we gonna do this? Let's create a new folder. Actually, no need. So let's just create another module inside of the render folder. So this is why I made them in folders. So the classes or the modules that only used, let's say, by the renderer, it could go into this folder called renderer. So here I'm gonna call this context. And kind of like an OpenGL context. That's kind of like what we're gonna make right now. But while in OpenGL, it just creates a context with using one function call. Here we are the ones who are gonna create the whole thing. Anyways, let's add this to GitHub, and let's have a pub struct context. Cool. And we're gonna implement the context, and so of course we're gonna need the window. We don't need an arc, actually. Yeah, we do need an arc window, yeah. And then what? Yeah, we're actually gonna store it here, in fact. And I'm gonna show you why in a second. Actually, no. Whatever. Let's see. All right, so let's start. Entry is equal to, and there we go. The NC spaghetti starts right now. Ash entry and Lloyd. We can say Lloyd, and of course let's make this a result, so otherwise we can have a lot of in wraps here. Let's use anyhow error. Sorry, result. Yeah, there you go. So we have an entry right now. This basically goes ahead and loads the Vulkan library dynamically. So basically the Vulkan library is a dynamic library in your system32. So if we go here to in Windows, at least you can find it in system32, and here if you search for Vulkan, you can see that your driver have a vulkan-1.dll dynamic library. So this contains some code for like as a Vulkan implementation by NVIDIA, I think, maybe, or maybe just a loader, I'm not sure. But anyways, so basically this entry right here, this code right here, would go ahead and load this dynamic library and fetch function pointers from it. That's basically what's going to happen. And in fact, if you click on this, control and click on it, as you can see, libpath vulkan-1.dll in the case of Windows. And yeah, that changes depending on the platform, right? So yeah. And if you check here Lloyd, the Lloyd function, yeah, it loads from Lloyd libpath, and there you go. It actually uses libloading function library to load the library. There you go. and then it actually loads the function pointers from the library that we're gonna use to call into the dynamic library. But yeah, pretty cool. It's called symbols. Last checked name lib.get name map. Anyways, whatever. And by the way, there is multiple things, like there's version 1.0, 1.1, all of these. So like, for example, entry function 1.0. So the first version only contains these functions, function pointers. There's create instance, enumerate instance, extension properties. And these are the types of the pointer functions. There you go. So they're in safe external system, blah, blah, whatever. Kind of got too deep into that. I'm sorry. Hopefully I didn't, like, what can I say? You didn't go crazy in that detail, but you don't need to know how that works actually. So yeah. Anyways, so let's say let instance is equal to, and here we're gonna say, honestly, instead of having insafe everywhere, I really do not have the patience for that. I'm just gonna do this, you know, a big insafe block. Not the best thing to do, but I don't care. So entry.create instance, and here in it pass in a address of, well, a vk instance create info, right? And it was builder like this, but now in a newer version it's actually called default. And yeah, so you could use two things here. You could either just fill in the struct directly, but I don't like that because kind of suck, because every time you have to give it the structure type that is needed for C, you know, because there's a spnext right here, which like you can actually chain the structs in a linked list fashion, right? And so that means that you can have a void pointer if you know C, which means that you don't necessarily know the type at that point. You don't actually know the type at all. You just have a pointer to the thing. So how are you going to know the type? Basically, you could go ahead to the first bytes, right, and see and cast that structure type and see what it is, right? So that enum would basically, like the first field in the struct would tell you what is the structure type. And then you could cast it to that type, right? And then you could use the fields however you want, basically. That's just a little detail right there. Okay, but I don't want to do this because otherwise, like if I use the builder thing, then it would fill for me the structure type itself. That's the first thing. And the second thing is that, let's say, for example, lists, let's say enabled extension names, for example, instead of having to give it like a raw pointer and an actual count separately, right? Just like in C, if I use the builder notation here, then it would actually do that for me. And instead of doing that myself, I would just pass in a slice, right? So, and it would do the rest, which is much safer, right? And much nicer to work with. So that's why I'm not going to be using this. I'm going to be using the builder, right? So default dot, here there's some few things. I'm just going to, we don't need all of this. We only need the application info. And even in the application info, there's a lot of other structs that you could search for in the documentation. Like you could just go ahead and say vk application info, right? And then you could like read until the morning, the next, well, actually not even the next morning, like the next year, right? About how everything works. In fact, you could go to the full manual, like it's crazy. It's pretty big. And there's even some crap right here, but anyways, whatever. So in my case right here, like basically not all the fields are needed, like required, I mean. So I'm not gonna fill all of them. Like for example, application info here, I'm only interested in the API version. The other ones are optional, pretty much. So application info, yeah, and I'm gonna say vk application info default.api version. So I'm only gonna fill in the API version. vk API version. I'm gonna use the latest API version. Pretty much. That may not be the best depending on your use case, but in my case, I don't care about compatibility. I hate it. In fact, a big reason of why like Vulkan is so bulky and hard and so on is compatibility, you know. Anyways, that's another story, I guess. What the heck is going on here? Let's see. Okay, it takes 2 parameters. All right, so the allocation callbacks, I'm gonna always say none. Don't worry about it. Okay, so other than that, we're also gonna need, in the instance create info, I'm gonna fill in the enable extension names. Now, basically, Vulkan, you could actually use it headless, meaning without a window. You don't need a window in system and so on. But if you actually want to use a window, then you need to add the extensions for that window in system. Now, in our case, since we are in Windows, we're going to need 2 extensions. We're going to use the Win32 extension to create a Win32 window, right? And we're also going to need the surface extension. This is the abstraction over all windows, right? Or all window types. So basically, you're going to have 2 extensions, the surface extension always, and a second extension depending on the system that you're in. If it's Linux, then it's going to be XCB or X11, and if you're Windows, it's going to be Win32 and so on. In my case, I'm going to go with, well, here where the Ash window library that I've told you about will come into play. So instead of me checking for every platform which extension I'm going to use and so on, no, that's for old people. What we can do is just Ash window, enumerate the required extensions, and just gonna unwrap that. And what this needs, this is gonna need the display handle, right? It's a raw display handle. Now, when it's beforehand in previous versions, it was actually giving a raw display handle directly, but right now it doesn't. It actually gives you a display handle. And then you have to extract from it the raw display handle. And I'm going to show you how to do it right now. Well, let's just actually do this, right? So I'm just going to say window dot display raw. In fact, instead of doing it here, I'm just going to say this raw display handle, right? And I'm going to extract it here. So raw display handle. So window, so instead of raw display handle like previous versions, you actually say display handle like this, and then you say the as raw. But let me first of all, to actually be able to use this, I need to import a trait called has display handle in this case, right? And then I'm gonna unwrap that result because there could be an error. And then to extract the raw display handle, I can say as raw. Okay, there you go. And now raw window handle. Let's extract that too, because why not? The AI missed this time. Let's just import this and say as raw. Okay, cool. Well, of course, we also gotta unwrap this, and there you go. Now we have the raw display handle and raw window handle. We can't pass in the window directly. Because like there could be like there's multiple window in libraries, right? So you want to support all of them. So what's the solution to this? How would you support all the window in libraries out there, like SDL, Winit, GFW, so on and so on? How are you going to do it? We have a raw handle, raw window handle. Let me show you, hold on. Raw window handle library, okay? So let's say you created your own window library and you want to actually use it, let's say with Rust, with the Vulkan and or with any other library that needs a window. How are you going to do it? You're going to basically go ahead, you're going to import raw window handle into your library, and then you're going to implement its traits, because this raw window handle basically just have an API and some traits and so on. and that you have to implement in your own library, and then anyone else can just use it, right? So basically a common window interoperability library for Rust. So it provides standard types for accessing Windows platform specific raw window handle and displays platform specific raw display handle. It does not provide any utilities for creating and managing windows. Instead, it provides a common interface. There you go. Like it's kind of like a Java interface, for example. That window creation libraries, when it's SDL, can easily talk with graphics libraries like GFX Hall, with WGPU, Vulkan, whatever. All right, cool. Let me check if the stream is fine. Seems good to me. Okay, cool. So let's continue. So here we passed in the raw display handle, and this basically would return for us an array, or actually not an array, a slice of const pointers to a C char, basically, right? So these are raw pointers, basically. But we don't have to worry about that here. Cool. Now we created the actual instance. Great. Next up, we're gonna need to create first of all, we need to load the extensions that we have included in the instance here, like the surface extension in our case. What apps are you making? Hello world. I'm not sure yet. Right now, we're just set up in the engine, or mainly the render right now. And we're gonna see what we're gonna do with it later on. I mean, you could tell me some of your ideas, pretty much. But for now, I don't really worry about that. We have a lot of technical stuff to handle before we get to reach that point. Anyways, so yeah, let's actually load all the extensions, because when you, let's say, create an instance, it will only load instance function pointers. But if you have some other extensions that you included, you have to load its function pointers by itself, like separately. So in our case, this enumerator required extension would contain the surface extension. So let's actually load that. Surface extension is equal to, now this also changed from previous versions. Now this is how you actually do it. Hash, right? KHR. Now it depends on the prefix of the extension. There are some extensions that have like KHR, which are the kind of official extensions, and the EXT and AMD, Android, etc., whatever. We don't care right now. Let's just say KHR. And these are the extensions that you can load, basically. Of course, as long as you have actually enabled them in the instance. So the instance is just an object that you basically give some information, let's say, about your application, about which Vulkan API version you want to use, which extensions you intend to use. So the driver could prepare stuff for you right there. But anyways, here surface, okay. And also the instance would actually fail if the extensions or some properties are invalid or unsupported, basically. So like, let's say, for example, if the driver doesn't support Vulkan API version 1.3, then it would actually return an error and you can't actually create the instance. And so the context creation would fail and so on, because we're propagating up the stack, the error, basically. Anyways, enough talking. Surface, let's see. So here there is the name, C string, and this is what we need, instance. New. And then you give it the entry and you give it the instance, basically. And then it would go ahead and load the functions for that surface extension. Now we could actually use this to access the functions of that specific extension, right? Though we're not going to need it to create the surface, because Ash, because that's basically platform dependent, right? It's not cross-platform the way you do it. That's why we're going to, again, depend on what is it called, Ash window, to do it for us, right? To handle that for us. So we're gonna say, well, not surface extension, we're gonna say Ash window create surface, and then we're gonna give it these stuff. We're gonna give it the entry, the instance, the raw display handle, and a raw window handle, and none for the allocation callbacks, as always. There you go. Now we have created surface, and as I said before, a surface is just like the the cross-platform abstraction of Vulkan over all the windows, right? So like, instead of having an XCB window and so on, all of them are abstracted as a surface. And so basically, we wouldn't have to deal with each window type it's by itself. We just have to deal with the surface, and then the Vulkan would handle the rest for us. Anyways, so let physical, now we actually have to enumerate all the physical devices, basically get all the physical devices that are available. In my case, I only have one GPU, though it could also give me though the, let's say the CPU and so on. Let me see. So you could just say dbj physical devices. And let's run this. Oh, let's say okay here. As you can see, the errors of Rust are very like the best out there. There you go. Okay, cool. Why it didn't log anything though? Oh yeah, we're not making the context be yet, so that's why. So let's actually do that. So the renderer would contain the context, would have the context, right? And then we're gonna create a context here. There you go. And then we could put it inside of the renderer. All right, cool. Now what? Yeah, I think we're good. Yeah, let's try this out. Though before that, let's just first of all store the stuff that we have here. And here's some detail that you have to actually care about. It's a little subtle detail, which is the fact that you have to make sure, now these unsafe stuff, like in here, create surface, if you see safety, there's a parent-child relation between instance and entry and the resulting vacant surface KHR. The application must not destroy. So as you can see, any unsafe function, any function in Rust that is, marked as unsafe, meaning that you have to ensure some of safety conditions yourself. That's why it's marked as that. So in this case, the safety is that the application must not destroy these parent objects before first destroying the returned vacant surface KHR child objects. Meaning that you shouldn't just, like, the window shouldn't get destroyed before destroying the surface. So the surface should be destroyed first, then the window, right? So yeah. So how are we gonna do this? And that's why I actually used an arc. So as long as the context is alive, we're gonna make sure that the window is also alive. That's the first thing. The second thing is the order of destruction of the fields. Now, the order of destruction of fields in Rust is, like, let's say you have field A, B, and C. So A would be destroyed first, B would be destroyed second, and C would be destroyed third. In C++ though, in C++, you actually would get the inverse order. And honestly, I prefer the inverse order better. I'm not sure why Rust did that, but anyways. So what we're gonna do, so the last field would be the hash entry because we created it first. What's the second thing is the instance. So as you can see, I'm filling the struct in the reverse order to make sure that the order of destruction is correct. But anyways, hash instance, what's next? And of course, you gotta store the entry, even though we're not gonna use it later on, probably. But you gotta store it. Otherwise, because the entry here is actually, if you drop it, then you would inload the library, right? And then if you try to access some function pointers from the instance and so on, you're gonna have a segfault, right? So that's why it's unsafe. As you can see here, safety DL opening native libraries is inherently unsafe. The safety guidelines for library new, blah, blah, blah. No Vulkan function loaded directly or indirectly from this entry may be called after it is dropped. So there you go. Anyway. So entry, instance, and then what else? We have the surface extension. and we have the surface, and then physical devices. Interesting. Now the thing is that I see is that for every renderer we're gonna load the freaking library, which is not something we'd like to do, honestly. Ideally we would want this instance and entry to be created only once for our whole application. Interesting. Well, we'll see about that soon. Anyways, surface extension, and then yeah, we'll see about the rest later on. And yeah, the window. Actually I'm gonna store it first before everything. And as long as the window comes after the surface, we're good. So the surface would be, well, in this case actually it doesn't even matter really, because we can actually implement drop to drop the surface, true. So it doesn't actually matter that much, yeah. Because the drop gets called first, then the drop of the other instances get called, or the fields. Anyways, here we're actually going to use the surface loader thing. Surface extension dot destroy surface, self dot surface, and none for the allocation callbacks. Perfect. Now let's actually fill in these fields, and apparently it didn't like it for some reason. Why? Oh, I see. Because this is outside of the scope. That's why. Add missing fields, and there you go. Now let's actually try this. And there you go. And as you can see, I'm getting, from both renderers, I'm getting what's going on there. As you can see, physical devices and so on. That's cool. So yeah. Yeah, cool. The other thing that I want to make sure I tell you before I progress with this is that make sure to get the Vulkan SDK, right? This would help you with like it would give you some tools to ease development with Vulkan, right? So you're gonna go download the Vulkan SDK, and depending on the platform, you're gonna choose one, right? So in my case, it would be Windows, and then I'm gonna basically install this SDK, right? So there you go. It's pretty simple to install. And then what you're gonna get is, if you go here, you're gonna get Vulkan SDK in your C drive, and there's some tools here. If you go to the bin, you're gonna find tons of tools like the DirectX compiler, and a lot of other crazy stuff like SPIR-V cross for translating between shaders and so on, SPIR-V reflect to do reflection on shaders. There's VKCube. You could test this to make sure that, you know, Vulkan API is working on your system. If this works, then it should work for you too, right? Just to make sure that Vulkan is actually functional on your system, basically. If this doesn't work, then you probably have a problem, right? So, and the other tools are very useful. It's VKconfig, and there's also VKVia. You could check it out by yourself, and Vulkan Caps Viewer, and Vulkan Info. So Vulkan Info SDK would give you information about your devices, though it's not needed if you have Vulkan Caps Viewer, and I actually have them here. So here's the Vulkan Caps Viewer. There you go. And this is basically, it would give you information about the devices, the Vulkan device that you have on your system and their properties. Now you could actually do this programmatically through some functions in the instance, right? So, but we don't need to do that for now. Like if you just want to check it out, you could do this here, right? But of course you don't know the users. So like if you have some requirements upon the device properties, then you have to do it programmatically, of course. So in my case, I have NVIDIA GeForce GTX 1650. It's a discrete GPU because like it could be a discrete GPU or, you know, what is it called? You know, those GPUs are usually in laptops that also have, no, sorry, CPUs that also have GPUs. So, yeah, integrated GPUs, yeah. Anyways, whatever. And some other properties here. Here's the features that are available for my device. The extensions, the formats, the key families, the memory, the surface, profiles, blah, blah. You got the point. That's the Vulkan capability viewer. And there's the Vulkan configurator here. Now, if you see some other tutorials, what they would usually do is that they would add some extensions here for debugging. Now, I think that's mostly, most of the time is just wasted time. In my case, I just use the Vulkan configurator. If I want to debug my application, I just go layers controlled by the Vulkan configurator. Actually, not extensions, sorry. It's going to be layers, right? You're going to add some layers programmatically, but I'm not going to do that here. I could just say this and then enable validation. And basically what's going to happen, if there's any problems with my usage of Vulkan, then it's going to tell me, you know. So in my case, there's no problem, at least not yet, apparently. There's also some other layers here, like for example the API dump, which is going to tell you exactly which functions are getting called and what it returns and so on, basically with the dump, what functions you're calling and so on. So like for example here, I'm calling vacay create instance and it's returning vacay success, which is basic success, right? And this is what I'm passing to it. Like for example, the extensions, I'm passing vacay khr surface and vacay khr win32 surface, right? And so on. So you could see the parameters and you could even get the pointers, so you could like use your debugger to see what those pointers contains and so on. There you got the point. For example, here you can see that Ash window actually called vacay create win32 surface khr because we are on Windows, and it passed the HWND handle of the window. That's for win32 API and H instance. Yeah, whatever. Just some tools there. There's also render doc, which would help us later on when we have some frames to debug. I'm going to show it to you later on. For now, we don't need it, so let's just keep it on validation and go on with our lives right now. Cool. So there's a lot of ways you could actually choose your physical devices. But for me, for now, what I'm going to do, like, I'm just going to select the first physical device. But let's just have a struct, okay? Pub struct physical device. And we're gonna store with it all the properties of the physical device, so when we actually want to use them later on, we find them, right? And so you're gonna have a handle here, which is the actual physical device, Vulkan physical device handle, and we could store the properties, right? So vacay physical device properties, the features of the physical device, the memory properties, and yeah, that's it for now. Actually, also we can also store information about the key families that are available in the device. So the key families are basically what you've seen here, key families. In my case, in my device, for my device, I have 5 key families. Now each key family have multiple queues, right? And each family is capable of some stuff, right? For example, the first key family 0 is capable of graphics, capable of compute workloads, transfer, and sparse binding, and it contains 16 queues, right? And it also supports presentation to the surface, because there is some key families that you can't use to present your frames into the window, right, or into the surface. And this one can actually do all of this. It can do graphics, compute, and presentation. So like you could use just this, you could use it for your whole application, right, for your whole render. There's also key family 1 here, which is only capable of transfer, and it have only 2 queues, and it doesn't support presentation to the surface. Key family 2, it only supports compute, and it also supports presentation. And key family 3, which doesn't support presentation, and it only have one queue, and it only capable of, well, actually it's capable of transfer and video decode. There's a new API in Vulkan which you could use to actually decode videos and encode them using Vulkan, like a GPU accelerator, right? So hardware accelerated. And key family 4 is capable of video encoding and transfer. So all of them are capable of transfer for sure. That's guaranteed. And this one doesn't support presentation. This one doesn't support presentation. So in our case, since we're just beginners, we're just going to go with the first key family for now, right? Because it's capable of everything. Now that's not guaranteed, but that's usually the case. So we're just going to go with that, right? And it also supports presentation. Okay, now in an ideal world, what I would do, like what's probably is going on here, is that this one, you know, it's capable of everything most of the time. The second one here, well, not necessarily the second one, but here it's only transfer and only 2 queues, so it's probably DMA of the GPU. So like you have fast transfers, like if you want to transfer big textures to the GPU, probably we want to use this key family. It's probably faster. Let me see if I could find some information about it. No? Is it called DMA? Yeah, direct memory access, I think. Not sure. But anyways, whatever. Basically, this is probably fast in transfer. This one can do compute and transfer. So I could have, for example, this key family here doing graphics. And then once it's done, I could pass it to key family 2, you know, to do some compute, like post-processing. And then this one could actually go ahead and present the frame, right? So the key family 0 could draw graphics. Then key family 2 could do post-processing on it using compute shaders, and then you could present it directly. But yeah, you got the point. Just some ideas right there. The other ones, I don't care right now. Anyways. So here, let's store some key family stuff. Key family properties, should I say? Or, yeah, properties. Key family property. Or, I don't know, man. Yeah, let's say key families, I think. Oh my god, analysis paralysis. Anyways, key family properties, pub struct. Anyways, whatever. So this is properties. And is there anything else? I don't think there is. Notice I'm using my AI to actually see if it can suggest anything, and then see if I want to include it. In this case, it only included properties. Yeah, and we're also going to need the index, though, of the family properties. Now, you could actually infer this from the index in the array, but that kind of sucks. So we're just going to include it here directly so it's easily accessible without having to make a separate iterator for indices. But anyways, cool. And by the way, these all will be public. These kind of like just info structs, basically. This one, yeah, this one too. Anyways. So that's, I think that's it. You know what? Let's just call it key families. Anyways. So, okay, cool. And here we're going to have public key families, vector of key families. Cool. So that's basically what we're gonna do. I mean, we don't actually need all these information, but you know what? If we ever need it, we're gonna find it here in these structs, which is great. So that's cool. All right, so how are we gonna do this? Let's let the AI do the stuff and see. Okay, so as you can see, it's using the instance to get the physical device properties using this function. There you go, the features, the memory properties, and the key families. There you go. Now here it's saying key families iter enumerate. As you can see, it's using enumerate to actually add an index to the iterator. And so it maps the index and the properties to key families. And as you can see, it includes the index into the struct, right? As U32 because it's usize. And then vector properties. Though instead of this, we could also say this. And I believe cloned, right? Because when you iterate over something, though actually we could just say into iter, I think, because we don't need these key families anymore, these key family properties. Is it? Yeah, we could just consume it basically. It exists for struct clone, but it's what? Oh, there you go. Cool. So that's pretty cool stuff. And let's just rename this to Q family properties, just to make it a little bit more clear. So we're mapping these key family properties, enumerating, and then doing, what the heck? Hold on a second. Why a vector here though? Huh? No. I think just properties. What the fuck? Hold on. What the heck? Why have vector? No, so like the whole key family have the same property, so all the queues there. We don't need a vector there. Okay, so it's the same name, we could actually do it like this. Great. And then we collect into a vector and let Rust, you know, imply that it's key families there. Cool. No need for this anymore. And okay. Let's actually call this handle, honestly. Why not? And we don't need to do this anymore. Cool. And honestly, we could just do this like this directly. And we should call this handle, yeah. Da-da-da. Great. Physical device. Now we could have used, hold on. I mean, actually we could do that, yeah. So we could say physical device is equal to instance enumerate physical devices dot map. So instead of having a vector and then, you know, like an iterator over, sorry, a for loop, we could just use an iterator here. And I'm just gonna say into iter because we're not gonna need that anymore. We could just consume it and remove it. move it, all right. So into iter dot enumerate physical, well, no, dot map, sorry, yeah. And let's see if we could, there you go. So the AI have realized what I wanted to do. Great, perfect. And now I could remove this crap from here. And there you go. Now I have a Vic of my own physical device struct that contains the handled physical device, the properties, the features, all of that cool stuff, right? And I can actually right here go ahead and print all of it. Print line physical devices does not implement debug. We could add derived debug to these stuff, so we could able to do that, I guess. Yeah, and for this one too. I don't think we need it for context, at least for now. And there you go. Now we could actually print all that data, all that information about the physical devices. Let's see. And there you go. Now, as you can see, all that data that we have seen in the Vulkan hardware capability viewer, we have done it programmatically, and now we could do whichever we want with that data. We could use it to basically choose which physical device we want to use, right? So that's pretty cool stuff. Like the API version, driver version, this is device name, as you can see, blah, 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 whichever. Anyways, for now though, I wouldn't do that much. The only thing I guess that I would do is to make sure that the physical devices are supported by the surface. So how are we gonna do that? We're gonna say physical devices dot retain. So this function in the vector, in vectors, it's basically you give it a callback or like a closure, and then it gives you all the elements inside the closure one by one. And then you have to tell it, do you want to keep this element or remove it? So depending on if this closure returned false or true, it would actually keep it or not keep it, right? In my case right now, the only thing I think I'm gonna do is check to make sure that it does support. Now, we could just use it like, we could just say filter, or sorry, find function to just find the first one that it's available. But later on, I want to be able to give the user the ability, let's say, to choose the physical devices. But I only want to retain the ones that I'm sure that they are supported, right? So I'm only going to give the user the choice of the devices that are, you know, suitable for the application. So here I'm only going to retain. Let's use the surface extension here. Dot get physical device surface support. Cool. But this would give us a result pool. So I'm just gonna say dot okay, honestly, or if it failed, I'm just gonna say, oh sorry, in wrap, or if it failed, then I'm just gonna say false, honestly. Cannot borrow a mutable local variable as mutable. Make it mutable, and there you go. Now, basically, this would only keep the physical devices that actually supports that surface. Cool. And now, what can I do? So what I mean by that basically is that we could have a callback here. We could have this struct context attributes, right? And then we're gonna have the window here, arc window, and we're also gonna have a callback, right? So a physical device, well, actually a queue family picker, right? And it's gonna be a callback. So I think I could probably just say fn physical device. So it's gonna be a callback, which I'm gonna give it every, actually, I mean, I could just give it the whole vector, to be honest with you. Yeah, let's just do that. Though I do need to keep it. So then I guess we could give it a slice instead. Maybe. Yeah, let's try that. So we're gonna give it a physical device slice. And then the user have to choose. And I don't like options. I always want my callbacks. I find it very annoying when I can't like propagate up the stack errors of results when implementing a callback. So I always, in my callbacks, I use result. But anyways, anyhow, result to be sure. But anyways, so result what? Physical device. Result physical device. That's the queue family picker. Okay, cool. We could just get maybe, I don't know. Anyways. So now what? Though we could call this its own type. Queue family picker. Type is equal to, there is another way of doing it, which is then callback, then something dynamic dispatch. But I think static dispatch is probably enough here. I could be wrong though, I don't know. Anyways, type queue family picker. I mean, it's the callbacks resolved at compile time, basically. So yeah, now instead of doing this, I could just say attributes. I really like passing all the arguments in a struct because it just gives you a lot of flexibilities like default values and so on. Anyways, context attributes here. Cool. Now we have to say attributes. Well, let's just say let window. Actually, yeah, let's just do attributes.window. And yeah, other than that, what I'm gonna do, I'm gonna store the attributes itself. This is another nice thing about structs, is that you could store them in the object. So whenever you wanna check out like what was the parameters that led to creation of this object, you could just check it out, right? Basically. So how are we gonna do this? I'm gonna put it. So instead of pub window, I'm gonna say pub context attributes. Context attributes. So like you could store the creation parameters, and you could even create a second context with the same parameters easily. Anyways, so that's it. Actually, what did I call it? Context? Oh, no, just call it attributes, I guess. Fine. And add missing fields, and we don't need window. So the window would be inside the attributes itself. It's fine. So this is another thing, is the fact that I don't have to extract and unpack all those parameters here. I could just store the struct itself. Anyways, so I think that's it for that one. Did I miss anything? I don't think so. Okay, so now we have filtered all the physical devices. We're going to use the key family picker callback that the user gives us of this module, and then use it to get a physical device, to pick a physical device from the supports of the ones that we have filtered and so on. Cool. And the user doesn't even need to worry about the Vulkan functions and so on. He would get all the data that he needs to choose the queue, like the physical device that he wants and the queue family that he wants easily, because all of it is inside of these structs. No need to call functions and so on. That's basically the idea about this. Anyways, next up, now that we have actually got the physical device, what are we gonna do? Yeah, actually we do not need that anymore, the physical devices thing. We only need the physical device itself. So we could just pass in the vec. We don't need the vector anymore. So let's just give it to the user, and then he could do whatever he wants with it. Like, I'm using a vec because I want him to be able to sort the physical devices too, which is very useful for picking out key family and so on. Anyways, so vector, actually I forgot about the key family, yeah, my bad. But anyways, we'll just say physical device, and then here he have to actually give me not just the physical device that he chose, but also which key family he chose. I mean, I could say index, but yeah, actually we probably want to do index. Or is it? I mean, it contains the index itself, so it's fine. If I do the index, you wouldn't understand, like, the user what the heck is going on there, right? So what is that usually to, right? But if I say Q family, it's way nicer that way. Actually, this should be called Q family though, not Q families. My bad. That's why the AI got tripped before and it did vector of properties. That's why. I see. Anyway, so it's a tuple of physical device and key family. Great. Perfect. Cool. So now we get two things. We get physical device and the key family. Great. Now, what's next? Now, by the way, you could also reuse this context module that we made here in your own renderer without any problems. I'm only dependent on winit here, at least for now. I'm only dependent on anyhow winit. and ash, so you could easily reuse it in your own thing. But anyways, so what's the errors that we have now? Cannot find struct key family. Yeah, makes sense. Let's actually say Q family. There you go. And what is the other one? Binding physical device. Yeah, okay, cool. Great. So now that we have picked the physical device, the key family, we have to create the device. How are we going to create the device? Well, before that, actually, it's not just one key family that we have to pick. Actually, we have to pick multiple key families. Because, like, as I said, you could have one key family for transfer, one for compute, and so on. Like, it doesn't have to be the same one key family. So for that, what we're gonna do, we're gonna have another struct once again called key families, and it's gonna contain all the key families that we have chose, right? So pub graphics, pub present, pub transfer, and public compute, right? And yeah. Though no, I'm not gonna do it this way. I'm just gonna I'm just gonna store the U32's indices. And I'm doing that because, well, actually, you know what? Fine, just store it. It's a little bit redundant. Who cares? Anyways, next up, gotta actually make sure that instead of doing that, gotta pass key families here. Now they could be the same. They could be the same thing, like the graphics and present, same thing, but they're just gonna have the same index. So yeah. Anyways, so this is basically key families. Yeah, that's correct. Great. So since they can be the same, and basically when we create a device, we actually have to give it only unique indices, only unique key families that we want to request for the device. So how we can make these unique to make sure that there's no duplicates in the key families, we could use a hash set here. So Q indices set is equal to, well, hash set, right? From iter. Physical device key families. Hey, what the freak? Oopsies. AK. The AI is kind of stupid here. So this is what it said. Physical device key families, right? The array. Basically he got the index from here, and then he used it again here to get the index. Oh my god, that's so stupid. Oh. But yeah, I get it why, because usually people do it like this. They don't usually have these redundancies that I'm doing here. So yeah, we could just do it like this. This is not an array, so I have to actually do it like this. I have to access every field, right? And now we're gonna have only the unique indices. And now what we could do is, actually let's call this key family indices, sorry. Indices set. Or indices, yeah, fine. And now I'm gonna map all these indices into actual Q device create info. So how are we gonna do that? Q create infos. There you go. So Q family indices iter map the index into, and I could say dot copied here, or I'm not sure what's the difference between cloned and copied though. Anyways, it doesn't matter. Q family index, or since this is a primitive, yeah, we could emphasize that it is just copied. It's not a big deal. This should be default and no need for build here. And we have the queue priorities. Now here, depending on the array of queue priorities, so like the count of this is how much queues you're gonna request. Now I could go crazy with that, but honestly for now, I'm just gonna assume, to make things easy on us, for now I'm gonna assume that we're only gonna be requesting 1 queue per queue family, right? And what else? And yeah, the priority doesn't really matter, is it 1 or 0, because there's one element, 1 queue, so it doesn't matter here. But cool, all right. So queue create infos. Now you could actually go ahead and create a device, finally. And we're kind of gonna be done with the context to, well, I guess to some degree. But anyways, create device, physical device.handle, and then vacate device create info, default, queue create infos. So here we're passing the queue create infos, great. And then enabled features, physical device.features. Oh, here it's actually basically enabling all the features of the device. Do I really want that? Probably not. You don't want to enable the features that you're not using. So I'm not gonna go that path. Right now I'm not using any extra features, so I'm just gonna keep this, you know, an empty array. So I'm only gonna provide the queue create infos. Perfect. So I think that's it. And then I'm gonna load in, well, actually I'm gonna need some extensions here. So as I said, because Vulkan can be headless, if you want to use an actual window, you have to first of all include surface extension, which is an instance extension, but there's also device extensions. And in our case, we're also going to need the Swapchain for the window to actually be able to present to those surfaces. So yeah, so how are we going to do it? Enabled extension names. Yeah, there you go. And yeah, so ash have been changed. It's no longer this way. You have to do it this way. Swapchain name. There you go. And .sptr, because that one gives you a C stir, but this one actually needs a pointer. There you go. So that's how you do it, pretty much. And I almost forgot, I want to also, I need to, okay, so I'm gonna be back in 5 minutes, okay? All right, back. Let's go. I'm not sure if that's 5 minutes or less, but anyways. Okay, so the mic is on, the camera's on, perfect. Okay, let's go back. All right, so cool. We have created device, perfect. Yeah, the other thing that I want to do here that I forgot about is I want to enable some modern features of Vulkan 1.3, which are dynamic rendering. So it would make our life way easier. And that's why one of the reasons I don't want to use WGPU anymore and so on, because you still have that bind crap, like that render passes and frame buffers and so on. Nah, I fucking hate it, man. But using some modern Vulkan features, like, your life would be way easier and you probably can get more performance out of it. Like, for example, render passes, they're not useful mostly for desktop. They're not useful. They're just, you know, it's just more overhead and more complexity of managing those render passes and so on. But with the modern Vulkan 1.3 core feature of dynamic rendering, you don't need to manage those render passes anymore. You just tell the actual GPU which image you want to render into, and it just does its job, you know, it does it, right? And of course you transition the layout of the image yourself and so on. We're gonna see in a second how that works. You're not gonna find this information anywhere else, especially in Rust and Ash, mostly. But you got the point. Anyways, whatever. Enough talking. How are we gonna do this? Yeah. So it's a device feature. So, but it's not a physical device feature. So how are you gonna actually do it? If I remember, you guys say push next. So here we're gonna use that pnext pointer, you know, that I've talked about before. And basically this is the way that you could extend structs in Vulkan, because, you know, Vulkan really cares about compatibility, you know, between versions and features and extensions and so on. So like if Vulkan wants to add, like the Vulkan working group wanted to add some new fields, let's say, into the device struct, right? They can't just go ahead and freaking add it to the struct itself. No, that's gonna break everything, right? So what they do instead, they give you a new, like a new extension, right, that you can enable, or that it could be a core extension in that version. For example, dynamic rendering is a core extension in Vulkan 1.3, meaning I don't have to actually tell the device to enable it for me. So I don't need to do that for that one. But if you're using Vulkan 1.2, for example, you have to actually say the enabled extensions and then include that as an extension. Here I just have, if I want dynamic render, I just have to include it as a feature. That's it. But yeah, that's, anyways, whatever. Default dot, let's see what we have here. No, that's not what I want. I want dynamic rendering features, not exe. That kind of tripped me last time that I did this. There you go. Not exe. Make sure it's not exe. So because this is a core, we're using the core feature right now because we're in Vulkan 1.3. If you were using Vulkan 1.2, then we have to use exe here. But whatever. And here we're gonna say dynamic rendering, and then I have to enable that dynamic rendering like this. And what the heck is going on here, dude? There you go. Cool. Lovely. Absolutely love that. The other thing is device address. Though I don't remember how do I enable it. Is it like an instance, or Let's see. So you could basically search up buffer device address extension, Vulkan. And then you're gonna get the registry, right? And then you can see the deprecation state here. It got promoted to Vulkan 1.2, meaning in Vulkan 1.2 and up, it is actually a core extension. So I don't need to enable it as an extension, but though I still need to enable it as a feature. But how? Buffer device address feature. Yeah, I think it's probably the same thing that I've done with the other one. Just basically do again push next, dot push next. Now if we're in C, we would have to actually add it here as a p next, but we have this useful utility here in Ash, which you just can say just push next and it would handle that for you automatically. This is if you want ray tracing, to enable ray tracing, but that's, I don't even have a ray tracing GPU. Unfortunately, if I had it though, I could have made a tutorial about it, hopefully. I don't. Right now, at least for now. Anyways, physical device. What is it called? Bind buffer? No, buffer device address, yeah. Again, make sure you do the one without the suffix because it doesn't work. At least last time I've done it, it didn't. There's also some other features in this struct. There's capture replay. This one, I think it's useful in debugging applications like RenderDoc. I'm not sure. I don't really know that much about these ones, but anyways, I intend to use them eventually if I can understand how they're used. So I'm here, I'm enabled them. Perfect, cool. So that's pretty much it, I believe. That's all we needed. What's going on here? Type presentation needed, hash set. Well, I thought hash set it. What? Interesting. Okay, fine. Then I see. So basically it does need a value. Like you can't ignore that. So yeah, okay, fine. We could give it that value, right? So yeah. Honestly, I'm just gonna copy that, and that, and just change that from. So there's graphics, present, transfer, compute. Graphics, present, transfer, compute. Okay, we can't use copied anymore. Interesting. Yeah, I could just do it like this. Index and... Or actually, I think I could probably get the keys alone. Isn't it? Can't I? Doesn't seem like it. I don't know. So let's just say index and key family pretty much, honestly. And let's just do it the regular way like this. I don't know why it didn't tell me about this before. EQ is not satisfied. What the heck? Why the heck the value should have EQ? Yikes, I don't get this. Maybe I'm not understanding the hash set right though. The implement requires. Yeah, I know the key should have EQ, but not the freaking. I'm very. Something is totally wrong here. Let's see what we got. Well, there you go. You can actually do it. No, what the heck? This is very strange. Hold on, go back. Go back. I think we had it right. I'm not sure what the heck is wrong with it. I mean, we could just say from, yeah. Oh, okay. So from, not from iter. Makes sense now. I was like, bro, what? Anyways, we're good now. What are we gonna do now? So let's add that device into the struct. Is there anything else we have to add? So we added the physical. Oh no, well, sorry, not here. Actually here, yeah. So we have added the surface up until now. What's next? We have the physical device. We're not storing that one. We're only storing the physical device that we have picked because we're not going to be using multiple ones. But anyways, we're going to store key family indices. Why not? We may need that. And of course, we're going to store the physical device in the key families. So let's start with those. Physical device and queue families and public. Right. What else? Key family indices and the device. So queue family indices and the device, vacate device. Yeah, that's cool. And we're also gonna need the queues. Yeah, we're gonna need to request the queues. So the queues would be a vector of vacate queue. Cool, lovely. Oh no, vector? Do we really want a vector? Yeah, it's fine. Yeah, that's good, actually. In fact, we don't want a hash map there. That would suck. Anyways, all right. So let's actually get the queues. And there you go. We're just going to use our queue family indices. And I'm going to map it to device queue. And we're just going to get the first queue because, well, we only have one queue anyway. So it's of course the first and the last. So it doesn't matter. Get device queue and we're going to collect it into a vector. Perfect. Now what's next? We're going to add those missing fields. And somehow the device is wrong. Or something is weird with the device. Why not? Yeah, because instead of vacate device, it should be an ash device. Apparently. Because vacate device itself is just the handle, but ash device also includes the function pointers. Yeah. And now that freaking works. Let's make sure we don't have any craziness going on so far with the validation. So the validation is on. And expected context attribute found arc window. Yeah, makes sense. Let's actually say context attributes. Oh, but it's not public, I guess. So let's make sure that it is public. Yeah, it's not. Let's make it public public, there you go. Now let's go back here and say attributes. Window is, well, window. And yeah, we need a Q family picker. Interesting. Now basically what's the point of this is that right now you could actually say that the Q family picker is basically like this, right? So it's basically a closure, and then you get the physical devices, right? And then you could do whatever you want, and then at the end of the day you just want to tell me which one you picked, right? Here what the AI tried to do is physical device editor find. Okay, so here it's tried to actually find a discrete GPU, because discrete GPUs usually are the most performant, you know. And then the Q families, it make sure that you contain graphics, compute, and transfer. For now, I'm not really gonna bother too much with this one. Maybe we could revisit it later. But for now, I'm not really gonna bother too much. I'm just gonna pick the first physical device that is cannot move. Don't move. Yeah, we could just do this. And next, the Q families. So I'm gonna pick one Q family for everything for now. Not gonna overcomplicate it right now. Key families. So we're gonna go through the physical device key families, and then we're gonna find a key family that supports all of the stuff that we need. We don't need to check if it's transfer, because all of them are transfer. We're just gonna make sure that it graphics, compute, and also yeah, that's it, I think. Right, so we want both in the same one, and then we're just gonna say Q families. We're gonna basically give it to all of them. Yeah, pretty much simple as that. So yeah, this is very simple. One, and yeah, finally, okay, cool. And instead of in wrap, we could here just say this inside of the callback, which is great. That's it, I think. Now, what's wrong with this? Consider giving this closure an explicit type, but why? That's strange. Oh, maybe it actually just needs it because the closure is there. Yeah, maybe if it was inside of there, like maybe if it was directly into that spot, then it would infer the types, all of them. But what the heck is happening right now? Hold on. What's wrong with this? Well, first of all, this is wrong. Q flags compute. So basically I want to copy this from here and do it like this. Yeah, now it no longer asks me to give it the type, which is great. Type mismatch. expected physical device but found cannot move. That's strange. But I mean, if I'm cloning it, then what's the problem? Yeah, maybe I need to make sure that it's clonable. Yeah, probably. Clone. Do I really want to clone it though? Actually, no. Why can't move it though? Hold on. If I say into iter dot next dot in wrap, would that work? Yeah, that works. Now I don't need that clone anymore. Perfect. And the can only use result. Here, since this is an option, not a result, we cannot propagate it back into the caller. But we could actually say use anyhow context. Though I'm going to say as anyhow context because we have another struct that is called context. And this is just a trait, doesn't matter what it's called anyways. You just have to be imported one way or the other. And now here, if we want, we could actually say the context, no suitable key family found, and then we actually get a result out of the option, and there you go. Perfect. Key family. Now the key family, yeah, should also be the same thing. So key family should be clonable, basically. I'm not sure if I really want all these redundancies. Maybe not. Because cloning all these crap is crazy. I mean, doesn't really matter since it's just initialization, but yeah, whatever, fine, who cares right now. I cannot move because it is... What the heck are you talking about? Oh. That's strange. Cannot move out to a physical device because it is borrowed. But yeah, it's borrowed here, but it's done. Oh, because the key family is still borrowed. I see. I see. Okay. What we're gonna do for this, it's pretty simple. Clone again. Though honestly, it's kind of a... Maybe I'm gonna make these key families honestly just U32s really. Kinda suck to clone all that crap. So yeah. Now if we do it that way, what we have to change, let's see. We no longer need to do this. And what else? And we no longer need to clone anything here. And we only need the index, so we're gonna map it to the index, isn't it? Using clone on type. Oh, we don't need the clone anymore. And yeah, there you go. That's great. Perfect. Field context is never read. Okay, fine. So that's basically the idea here. So as you can see, the renderer itself gets to easily pick which key family it wants and so on in a very easy way. Though to keep things like, if this was a library, you know, it would be nice. Let's say if you had, but anyways, whichever, I think, or yeah, we could do that. Here's my idea basically. If this was a library, what I would do is I would actually pick this thing right here and make it some like a default kind of thing, right? So you would have, let me show you. So let's go back to the context, right? And I'm gonna have a mod, like a nested module in context. Pubmod physical device, or we could even have a separate file for it actually, but anyways, queue family picker, sorry. So queue family picker, and you're just gonna have, well, we're gonna paste in that guy, and I don't know why the heck it's like this. That sucks. But I'm just gonna say fn, let's just say f, whichever, right? And then physical devices, vec physical device. So you're just gonna make sure, well, vacate physical device. Actually, no. Physical device that is here, yeah. Cool. All right, and we do need anyhow context, yeah. Though I gotta make sure to, where's the anyhow context? Here you go. Has anyhow context. And we gotta import the queue families too. We're gonna import vk here. Okay, what's up at semicolon? Oh, my bad. I see what's going on. So this needs to be results. Physical device, yeah. Well, actually, queue family. Queue families, well, first of all, physical device, yeah, comma queue families, tuple. It should match the type of the callback. Well, of course, here I'm gonna say use anyhow results. And let's just call this, let's give this a picker name, like single queue, I guess. Queue family picker single queue family, because we're gonna pick only one queue family that is capable of everything, right? So single queue family. That's what I call it. So like you could have multiple pickers here, and then the user could choose like whichever picker without actually implementing the whole thing again, basically. So here, instead of doing all that callback here, what I could do is single, well, it should need to be public though. I'm just gonna say single queue family, and well, first of all, picker queue family, picker single queue family. Then I have to import that, and there you go. You see what I mean here? There you go. Single queue family. Cool. So you could easily swap in the picker. Anyways, whatever. Remove the whole use item. Alright, so now we have finished our glorious context. Next up, we're gonna need, I mean, we still have some things to do, I guess. Well, first of all, I want to change something though. Which about the context, yeah. Which is the entry and the instance. These ones, I don't want them to be here. I don't want them to be created twice, for like once for every single like renderer. I want them to be created once for the whole application. So how I'm gonna do it? Also the surface extension, isn't it? Yeah. Yep, pretty much. So the surface extension, like all the extensions of the instance and the entry, all of these I want to load them once, isn't it? Well, hold on. Yeah, that's good actually. That's good. So let's go ahead and how are we gonna do this? I think I'm gonna have like a renderer manager, or like a renderer factory. What should I call it? Let's create a new Rust file. Render, yeah, probably render manager would be nice, I guess. Render, yeah, okay. Let's attach module, add struct render manager. So this would be like it would contain these stuff right here. So they are going to be created once. And since we have that, we could also remove that, like here where we have renders and hash map window ID, we could also grab that and we could put it here. Now this render manager would basically contain everything that is going to be shared between renders, right? It's all the resources that are going to be shared there. So that's cool. I'm not sure if we want it to be public. No, I don't think so. The entry though and the instance, probably. I mean, fine. Though I don't think we need the entry. Only the instance and the service extension. These are the ones that should be accessible though. And there you go. Now what I'm gonna do is I'm gonna go back to these context right here. And I'm gonna get this entry. Oh, but the thing is, the problem with this is that to be able to create the instance, you need at least one window. Just, yeah, what I'm gonna do is I'm gonna get at least one window and then just create a dummy surface just so I could check for compatibility with that surface. Yeah, that's what I'm gonna do. We probably also, do we? Hold on. Do we forcibly want the same physical device? I don't think so. It doesn't matter, probably. Yeah, unless if we're gonna be sharing resources between renders somehow. For now, let's just cut this out here. So impl render manager. I just realized I should have probably called this engine development instead of, you know, Vulkan for beginners, but anyway. So we're gonna do this, and we're gonna have here, though we don't need an arc window because we need the window just temporarily. We don't need to own it, right? So we're gonna destroy immediately afterwards. So we're just gonna have a window, sorry, just a reference to an arc window, basically. Or even just reference to a window, but anyways. Window ash vacay. No, we need window. And I could probably just get it out from there. Yeah, I think so, maybe. So maybe we could just do it like this. Actually, yeah. Of course, we do need an unsafe block. And then finally, okay, self, right? And then renders would be a new hash map, right? Now we got the window here. We're just gonna get the display handle. So we're gonna need to import that trait. Same thing here. Import that trait. And yeah, so now that we got the surface, well, actually, well, we're gonna need the surface only if we gonna pick one physical device for all of them. Let's see what AI would say about this. Is it a good idea to use only one physical device for all renders? Yeah, honestly, true. Yeah, so we're gonna pick one physical device then. So we could pick all of this stuff of physical devices. Even the Q families? Yeah, even the Q families. Now the only thing that would be different between a context and another, like between each renderer, is a device. Though coming to think about it, why would we need a different device for every single window? Yikes. Why would we need a separate device for every window? Like, why not just use one device for all of them? Yeah, so then the renderer shouldn't actually contain... Actually, so the context is correct. It's just... what the heck? Yikes. So we don't actually need a renderer manager. Yeah. Well, that sucks. I see now. So every renderer shouldn't really contain a whole new device, right? So it should only contain the swap chain and stuff that we're going to create after the device, right? So the context, we're only going to have one context. My freaking bad. Yeah. I mean, yeah, we could have multiple devices, but why bother? Right. Though the nice thing about having multiple devices is it may make parallelism better, like easier, sorry. And no. So I'm gonna keep this as it was before. Yeah. So I'm gonna keep this context as it is. And I'm actually gonna remove this render manager crap. Delete anyways. And so we have now the context, perfect. The only thing I'm gonna change right now is the fact that no, it's not gonna be the context like this. So every render would have an arc of context, right? So basically they're gonna share the same context, and they're gonna make sure that the context live as much as all the renderers. That's basically what I'm thinking about here. Correct. Yeah, pretty much. Seems about right. Expected arc context but found context. So we're not going to create the context here. Well, yeah. So window. Yes, window, but also the context. So we're going to say context, arc context. I mean, you could create multiple contexts if you really want to. And so, yeah, cool. Cool. So now, how it's going to be like is, we're going to create the context in the engine. The rendering context. I should probably rename it as a rendering context, actually. Yeah. Apparently this doesn't seem to be able to import it. Interesting. So I could just put it with the engine for now. Yeah. Should probably rename to rendering context. And now I could actually import it. Import and import. Cool. Though, as I said, I'm gonna rename this honestly to rendering context, just to make it more clear. Same thing here. Rendering context attribute. Of course, I'm not just renaming this one, I'm actually renaming like the symbol, so I'm refactoring the whole thing. Anyways, this function takes 2 arguments now, basically. So let's actually have this in an arc, so it could be shared. Yeah. Now every renderer would get, you know, a new key to the arc to the rendering context, right? So rendering context got clone. So we're cloning the key, not the actual object itself. expected expression. Okay, cool. That's perfect. Now I need to yeah, let's actually add those renders back, please. There you go. And yeah, that's it. Great. One true blue, welcome to the live stream. So this one also same thing. Let's just use self.rendering context. And so that means we have to also include the rendering context here, of course, an arc to it. Yeah. And so we need to include it here, and then cannot move. Well, that makes sense. I guess we have to clone the arc. And yeah, there we go. Perfect. Cannot find value window in the scope. Huh. Which window? Oh yeah. Though we have already created the primary window, right? Yeah, so we could use that to create. Hold on. So that's an arc. How can I as ref? Oh, expected. No, not anymore. Actually, the heck I'm talking about. Yeah. So as I said, we don't need the render context shouldn't have any surfaces. Yeah. Shouldn't store any surfaces. That's the job of the swap chain that we're gonna create, or sorry, the renderer, the actual renderer. So what we're gonna do, we don't need an arc anymore. We only need a reference to a window. And of course we're gonna need some lifetime. And it doesn't matter, okay? And now I just gotta make sure one thing. So after I'm done with the surface, I have to destroy it, okay? Because here I'm using the surface to check for compatibility. So this is kind of like just a dummy surface, right? That I'm using over the primary window too simply. Right? Am I right? Yeah, there you go. So I'm doing it here, right? So after this, I'm not gonna need it anymore. Yeah, true. So I could go ahead, and in fact I should make sure to go ahead and say surface extension.destroy surface. That's why I don't need an arc of a window, I only need the reference, because I only need it temporarily. Because after this call ends, like after the render context ends, I'm not gonna need it anymore. So destroy surface, and there you go. So this is just like a dummy surface, and just to make sure that's clear, I'm gonna say dummy surface, or to be compatibility surface. Right? And to make it even more clear, we're gonna do the same thing here. Shift F6, compatibility window. Kind of like WGPU, if you know that. Compatibility window. And yeah, there you go. Yeah, that's pretty cool. This is lifetime specifier. Oh boy. No. Well, nah, I ain't never gonna do that. Is there another way? Yeah, actually, I don't even need the context attributes anymore. Nah, that's useless. In this case, at least. So yeah, pretty much. No such field as attributes, yes. And no field surface in, yeah, we don't have that anymore. Cool, perfect. Now let's make sure to implement the destruction of the context here. So destroy device. What the fuck is this AI is doing? It's using service extension to destroy instance. What the heck? Anyways, self.instance dot destroy instance. Too simply. There you go. So of course we need to make sure to destroy the device first and the instance, pretty much. And there you go. That's too simply it. Oh boy. Anyone could reuse, like if you don't want this project, you could just reuse this context thing. It does have a lot of assumptions, but like a lot of it generic, and hopefully it could make it even more generic in the future and maybe turn it into a library, I don't know. To cut down on the freaking because this is a process that you have to do for every single Vulkan application. Nothing really that special, you know. It's just that I'm making some assumptions. For example, one of the assumptions I'm making, I'm not caring about a compatibility with Apple devices. Yeah, because for those you need to add some stupid compatibility extensions and so on. I mean, I could do that. I'm just too lazy to do that. And the other problem with that is that I don't think Apple devices supports 1.3 yet. I mean, the thing is about Apple, they don't support Vulkan natively, so you need like Molten VK, which is like a translation layer to Metal API. So because basically Apple have their own API and they refuse to use anything else, so we have this translation layer called Molten VK, which basically takes those Vulkan calls and translate them into Metal calls, and basically takes the shaders in SPV or SPIR-V format, which is the shaders language of Vulkan, and converts it into the shader language of Metal, and so on and so on. And I don't think they're supporting 1.3 just yet, and even if so, let me see. Molten VK. There you go, 1.3, 1.2. So they still haven't reached 1.3, just a lot of freaking work to, yeah. So as you can see, it's a layered implementation of Vulkan 1.2. So for now, sorry, no macOS. Fun fact, Asahi Linux on your MacBook supports 1.3 natively, but macOS needs Asahi Linux. That's interesting. But yeah, for now, no macOS. Though you could use it. You could use it if you just go with 1.2. But then you're gonna miss out on dynamic rendering unless if Molten VK already supports that extension. So either way, you're gonna mind your own business if you want to support macOS. For now, no macOS. Because it's just a pain in the. You got the point, right? Like if I want to actually support macOS, I'd rather just freaking make like new code for Metal API, you know, instead of trying to shoehorn Vulkan into Metal. Into macOS. So you got the point what I'm talking about here. Other than that, yeah. What other assumptions I'm making until now? I'm gonna make more assumptions, but until now in my design of this context, what I'm making, yeah, the fact that the API version 1.3, yeah. What else? The fact that we're using only one queue per queue family. So here's the assumptions we're making. Just to be clear, let's actually do it like this. The thing is, I think all programmers actually really, at least for me, I really enjoy having some component that is truly generic. But the thing is, the more, even mathematicians really, yeah, why you have all that crazy theories, you know, like not theories, but like demonstrations and so on. But whatever, like the more generic the thing is, the more fun, right? But the problem is, the more generic, the more it's harder to do, right? Harder to implement, first of all, more complexity, maybe even less performance, right? So yeah. Anyways, the Vulkan instance is created with the Vulkan instance. Okay, AI is good, great. Vulkan instance is created with the required extensions. Yeah, currently, yeah, we're not gonna add any extensions. Only the required extensions. It's created with the required for the surface. Whichever. Yeah. Yeah, we're assuming that we're gonna be using these features. The AI actually realized what's the assumptions. Crazy, cool. For the physical device surface support. Okay. I'm just gonna let the AI dream all of the assumptions that it thinks, and then we're gonna filter them off. Nah, just freaking, nah. It's just dreaming at this point, right? So no, it was good up until here, right? So dynamic rendering on buffered device address for now. We're probably gonna add more features and maybe even more extended later on, but this is what we have right now. We're assuming that that's the case. No, this is nope. It's create required extensions for the window instance. Only with the required extension for the window. So yeah, these are, I think, the only assumptions we're making until now. So that's cool. All right. So now we're finally done with the freaking rendering context. Okay, crazy. This is kind of like the OpenGL context that you easily get for free in OpenGL. Now we have to create it ourselves. How much lines of code? I mean, it could have been way smaller if we just decided to just freaking pick the first physical device and go on with our lives, and the first key family, who cares? But yeah, it's a bit generic there. Cool. Next up, we're gonna need the Swapchain stuff, and the Swapchain is quite interesting. We're gonna actually start with the render, basically. So, and I'm actually gonna rename this though. Hold on. Refactor, rename. I'm gonna call this rendering context, because right now it's actually in the engine. It's no longer in the renderer folder. Now the renderer, as you can see, have a handle to the context. And by the way, let's actually try to run this. Whoopsies, what's going on here? All right, so move occurs, compatibility window. Value borrowed after move. Okay. So let's do that before we move the window. Now it works, perfect. Yeah, great. Let's make sure we have no problem so far. So validation. There doesn't seem to be any validation errors so far, which is perfect. Great. Hold on though. Yeah, that's cool. That's great. Now, what's we gonna do? Next up, we're gonna create an actual swap chain. So in the swap chain, it's not gonna contain just the swap chain, but also the surface. That's just my own design. I think it makes total sense to have both objects in the same object. Anyways, so let's see. Hold on, let me think a bit. The thing is, the swap chain needs to be able to be recreated, but the swap chain itself could handle that. Yeah. Okay, fine. What else are we gonna have in the renderer? Yeah, we're gonna have pipelines. No, the pipelines, I think it could be even the... We'll see. Let's not think too much right now. Let's just create the swap chain struct. Cargo crate, no, Rust file. I'm gonna call this swapchain. Add. Is the stream good so far? Is the stream good? No dropped frames, perfect. It's already 3 hours just in the freaking context. Interesting. Anyways, let's go with struct swapchain. Now here we're gonna have a few things. The first thing that we're gonna have is the surface. So with vk surface, the surface that we've created in the context was just there to check for compatibility. It was just a temporary surface, right? So we can check for compatibility. Now we're gonna actually create the actual surface that we need. And with that, we're gonna need to store an arc to the window. Yeah, pretty much. Instead of just a reference, basically. And yeah, it's actually khr, yeah. Cool. And now pub, let's make sure that we got the window here. Arc window. Oh, what the freak? Window. There's some weird imports there. Anyways, so we have the window and the surface, and what else? And we're gonna have finally the actual swap chain. Since this is called swap chain, let's call this handle instead, because like this is the Vulkan handle, not the actual swap chain, but you got the point. Okay, and we're also gonna need the images of the swap chain, and we're gonna need the image views too. And it would be useful to have the extent and the format. Though actually not all of this should be public though, there's no need. Yeah, probably none of this needs to be public, except maybe for the window here. We'll see about that. But for now, only the format, the extent is the ones that would be useful for other renderer components, right? Like for example, when we're going to create the pipeline, we need to give it the format of the image that we're going to target, right? So we're gonna get it from the Swapchain. That's why this is public. All right, cool. So let's implement the Swapchain. Alrighty. Oh, Swapchain. Okay. Swapchain. That's a cool name, honestly. FNU. I'm gonna have result. And okay, and we're gonna pass in here, we're gonna need the arc window. Pretty much. Now, wrong number of type arguments, expected 2, found 1. Well, sorry, result of self, yeah. Here, self. And let's go and get it. So first of all, we need to get the surface properties. And oh, no, we're gonna need the context too, though, of course. In fact, we need an arc of the context, yeah. If it wasn't for the context in one struct, we would have to pass in the freaking device, the instance, the physical device, the surface loader extension. Just a lot of crap. Oh, I forgot, we need to create the surface first, yeah. Okay, the rendering context. There you go. And let's start by surface. We need to create the surface. So context.create surface. Now, ideally, we don't want to actually access anything from the context directly. We actually just want to make some functions that would actually help us do that in the context itself, which would be cool. So, okay. So let's go back to the surface. Sorry, the context. Where is it? There you go. And let's create a new function called create surface. Pub fn, yeah. And it would just get a that. And honestly, this does make sense to make it unsafe, really. And the safety is basically not that. The window should outlive the surface, basically. And we don't need unsafe here now. It's basically just like the other one. Just like the safety of this guy, right? I mean, if we actually check this, this is how you do it, yeah. I mean, we could just copy this whole thing and put it there. But honestly, nah, let's not worry about that right now. Extern. It's probably pop in safe fn like this. And now what? In used result. Okay. Result, VK services, mesh types. Alright. Let's just say okay. And unwrap that thing. Yeah, that's it. And notice that here we're getting the self entry and self instance. So like the Swapchain doesn't have to care about the entry and the instance both and all that crazy stuff. You only have to worry about this guy. Anyways, so right now context create surface calling to an unsafe function. So this is an unsafe. I mean our whole application is unsafe, but anyways, let's just do it here. So we kind of like most of the unsafe code is in the context, basically. But anyways, now what? So we created the surface, and now we're gonna need to get the capabilities of that surface. So surface capabilities. Oh yeah, we have to create another function now. Oh boy. This is gonna be a lot of fun. Cool. I'm glad that I have the AI. At least it kind of helps here. Perfect. As you can see, we get the physical device handle, and we get the surface capabilities. Perfect. What else? Expected to. Okay, so let's use anyhow results. There you go. Okay. And what else? So we got the surface capabilities. We could even get the surface formats. Actually, I should probably do something similar to what we have done in like the thing that we have done for the physical device. It's like we collect all the information in one struct and then we give it to the user of the function, right? So with that out of the way, this create surface here should actually do all that for me, right? So basically what I'm talking about is that we're gonna have a new struct surface. They would have the handle, and then it would also have the capabilities stored and formats that are compatible, right? Let's just see, okay? Let's go ahead and do it here. So this is the surface. Whoopsies. And actually this would just become the regular result, yeah. So result surface, right? So this is the actual handle. So let handle is equal to this. And of course we're gonna do this like that, and there we go. Cool. So we're gonna actually say okay, surface. Expected surface KHR, but found surface capabilities KHR. What the heck? So this is the capabilities is equal to this. Oh, what the? Oh, my bad. I see. Oh my god. So I was actually wanting to do it here in the create surface here. All right, let's do the capabilities, and then let's go with well, this is the actual handle, yeah. So let handle is equal to this, and then we're gonna pass in the handle here, and there you go. Now we're gonna say result of surface pretty much here, and we're gonna say okay, surface handle capabilities. There you go. All right, so what other informations we can actually gather about the surface? There's surface capabilities, surface support we already have kind of checked about that. So we have the formats and the present modes pretty much. So vector of surface formats KHR and vector of, yeah, so we have formats and present modes. That's what we have other than that. So formats, come on, and present modes. There you go. That's great. Perfect. So let's actually get all the information and put it in one struct. I actually also inspired this design from Volcano. So the actual safe Volcano wrapper. Here, we're not really caring that much about safety. I kind of, to a very limited degree, honestly. But yeah. I'm just like not religious about safety here. While in Volcano, no, that's not the case. And also not just safety, but other stuff. Like I'm just using the actual structs that comes in with Ash. But in Volcano, you actually get everything new, everything shiny. Like everything is a new struct, everything is. So like you just don't deal with Ash at all. But that's not my goal here, right? So if there's anything I could reuse from Ash, I just do it. So that's the thing. Nested fields and surface initializer formats and present modes, and there you go. So there you go. That's what I'm talking about. So instead of having one function after the other, in this context, we have everything in one function. Perfect. Cool. And of course, it should be public though. Because it's like an informational structure in some sense. Okay, cool. For now, I really don't have the energy to do all that freaking filtering of formats and stuff like that. So for the format, honestly, I'm just gonna, right now at least, I'm just gonna force in the sRGB format, okay? So vk sRGB format, right? I really do not have the energy to go crazy with that stuff right now. So bgr8 sRGB, and the extent, we're gonna take that from the surface capabilities, okay? So surface capabilities, the extent, current extent, and the other thing, the image count is minimum image count plus 1, though the minimum image count, if you check the what is it called? The Vulkan spec, yeah. It could be like in Linux. It could be. There is something about it. Yeah. Don't remember though what it was. You know what? I'm just gonna ignore it for now. In fact, in these two, the extent and the image count, to do not Linux really, to be clear, Wayland, I think. Yeah, Wayland. I mean, we could fix it now, in fact. Oh, well. Actually, you know what? We already have the window now. So why well, if you don't do it this way, then it would kind of gives you some errors. I mean, we could do it fine. Like the AI could probably help us here. No. If surface.extent, well, the current extent. Oh, sorry. Capabilities.current extent. Yeah, exactly. Exactly. Great job. So if service capabilities current extent width not equal to U32 max, because in Wayland it actually gives you maximum. If that's not the case, then we're good. We're gonna get the current extent. Else, if we are on Wayland, then we're actually gonna get it from the window. And there you go. Pick extend 2D. Cool. So that's perfect. For the image count, oh, I see. I remember now. So we're gonna clamp this. But I don't. Oh yeah. Maximum image count dot. Like basically, no. What was wrong with maximum image count? Let's check the spec real quick, actually. So we could check basically the capabilities. There you go. Maximum image count is the maximum number of images the specified device supports for Swapchain created for the surface, and will be either 0, okay? So this could be 0, or greater than or equal to minimum image count. A value of 0 means that there is no limit on the number of images. There you go. So basically, if this is 0, there you go. So if it's 0, then we're going to give it U32 max. Otherwise, we're just going to give it maximum image count. Perfect. And that's basically it for the image count now. Now, we made sure that Linux stays in the line for now, at least. Image usage. I don't, no need for that, I think. Okay, cool. Now let's actually create the swap chain. But now we gotta actually think about some stuff though. Yeah. We gotta think about recreation from now, actually. So the surface is great. Perfect. The swap chain though. Format, extent. Nah, actually this is fine up until now, we're good. Format, extent, and image count. Yeah. So format, extent, and image count. Well, this is not the actual image count. This is just the desired image count, right? Because the actual driver is free to actually change it. So yeah. I think so. Anyways, desired image count is that. Desired, so just extend the format. Yeah, that's it, I believe. For the image views and the images, it would be just MTFX for now. And for the handle, we're just gonna go with a null handle for now. For the surface, no, it should give me a surface. Because, yeah, I see. I mean, actually, if that's the case, can't we just... no, we're good. Yeah. So, surface. And the handle is default. Perfect. Yeah, that's it. Now we actually gotta say fn on resize, like self.window.inner size, self.extend. update size. Oh, it's the same thing actually. Anyways, whatever. So now let's actually create the swap chain. So new swap chain. Let the AI do its job. And let's see what we got here. No field context in type mutable swap chain. Oh, we're not storing the context then. Interesting. Let's actually store it then. Arc rendering context. In the window, we're already storing that one, so good. Good. Missing field swap chain, initializer context. Add missing fields. And there you go. Now, not the device. Here we need to access. Well, actually, as I said, yeah, we shouldn't do this here. We should do in the context itself. So basically, I'm just gonna. But does it actually matter in this case? Yeah, fine. It's fine. Let's just remove that none. I don't care about it. Expected U32. Yeah, so it's, I guess, vacate true then. Yep. Oh, I see why that's the case. Because it's using not the builder notation. Makes sense. Mismatched closing delimiter. Whoops. Yeah. Okay. Let's go to here, yeah. And let's just say pub fn create swap chain. Oh my. And we're just gonna say result vk swap chain khr. This is just the handle. It's just gonna create the handle. Well, actually, no. It's just gonna be like, instead of surface, it's gonna be create info really directly. It's just that so we can hopefully remove those publics from all of those attributes essentially. So vk char create create info kchar, yeah, there you go. Now it should do it. Not found in the scope. Oh well, it should be swap chain extension. Oh yeah, we haven't loaded that one yet. Cool. So after the device, you can say swap chain extension kchar dude. There you go. Cool. And then we're gonna include it here. Add that field. And this is gonna be ash khr swap chain device. And there you go. Well, the order should be after the device. Why not? And then what? Okay, cool. Now let's say Swapchain extension, create Swapchain. And yeah, honestly, in this case, it's just gonna be ash prelude fake result. There you go. And there you go. It's as simple as that. Nothing fancy for this one. The fancy stuff would happen here, basically. Okay, what's going on now? Oh. It's fine. Do it like this then. There you go. Cool. Alright, so as you can see here, I'm saying all swapchain self.handle. Now, if this is the first time we're going to be creating the surface, sorry, the swapchain, then this handle would already be null. So it's kind of like we didn't set all swapchain. It's already a null handle at first, which is great. So this is like the new swapchain basically, because we may have a, like, if this is the second time, like not the first time we resize in the swapchain, then we already have a swapchain created. So what I'm gonna do after that, I'm gonna actually destroy the swapchain. So destroy, oh sorry, call text, we'll destroy swapchain self.handle. Though to be honest with you, I feel like I'm probably just overshitting doing this one. Like shitting. That's yeah, for real. No need, honestly. Break it. I mean, I do want to not, but yeah, I'm gonna waste a lot of time for no reason if I do it that way. So let's just do it this way, dude. Swapchain extension, create swapchain, and then basically just say in save block here, please, and there you go. Great. Yeah, let's just do it this way. There you go. And here again, swapchain extension, destroy swapchain. Too simply. So we're destroying the old swapchain after we create the new swapchain. It needs it so we can reuse some resources, I guess. But yeah. We're also gonna destroy, we can't destroy the old images because they're not owned images. But the image views are owned, so we are the ones who create them. The images, we just get them, as you're gonna see in a second. So after that, we could destroy the swapchain. But before destroying the swapchain, I guess we should remove the image views. Yeah, makes sense. So for image dot drain, ooh. So this basically would remove all the image views from that vector and would leave just an empty vector. Pretty cool. And then it would give us back that image views, right? As an owned image view, right? So no reference there. Perfect. I actually can just say for each image view, context destroy image view. Perfect. Lovely. Alright, so other than that, for the other one, for the images, since we don't want to destroy them, we're not owning them, we're just gonna clear it. We're just kind of like just forget about it, right? So the images don't clear. Then we're gonna destroy the swapchain, right? And now we can create the new ones. Well, after that, first of all, let's assign the handle to that, the new handle. And then we're gonna get, as you can see, we're getting the swapchain images. We're not creating them. Actually just say directly self.images though. What the heck are you doing? Oh boy. There you go. And finally, we're gonna create the image views. Now the image views are interesting. This one I'd like to create a helper function for this one, really. So rendering context, cool. Pub in safe fn. Actually, no need for in safe. No, say create image view. Honestly, I'm probably gonna remove it from here too. Just like too much in safety. It's very annoying. Anyways, so create image view. We're gonna get the image, the format, and the aspect flags. Create image view. So image view type. So here we're assuming that it's a 2D image, right? Though you could go ahead and say image, we could like have that too. So like type, but we can't do that. So let's call it image type. Okay. There you go. So it's also, because they could be a 2D image, a 3D image, or a cube, or all of this stuff. Though honestly, if that's the case, you know what? I'm not gonna be using it right now, so let's remove it. Let's just keep it as a hard-coded value for now, because I never worked with 3D images just yet. So let's just keep it as it is. Component mapping. I'm not sure if the default is correct. It probably is, but I mean, I would assume it is. Otherwise, it's gonna tell me or something. We'll see. Yeah, it should be correct. Yeah. Format, good. Sub-resource range, honestly, I don't understand. I guess this wouldn't be that useful for regular images. But yeah, I'm just gonna ignore all of this stuff for now. The only thing that is interesting right now is the aspects flags. So is it a color image or a depth or a stencil or what? And then the format and the image itself. That's all for now that is needed. Later on, if we want something else, we could add it here, which is great. Now, let's actually use it. There you go. Perfect. Now, instead of this thing, we could also say images.iter.copied. Is just a handle. So .map image, so the context, create image view. Oh, and what about the result? Where did it go? Oh yeah, collect result. That's nice, but that's creating a new vector for no reason, dude. I do remember there was like a new member that could actually do that. .collect into or something, is it? Isn't stable, okay. So it's still unstable, apparently. Though I could try to add the feature and see what happens. Extend result. Oh, well, the problem here, first of all, where the heck did I add that feature, dude? Here we go. Let's just remove it. Ba-ba-bum. Yeah, try collect. Honestly, you know what? I don't care. Just say collect. Or we could just make it regular freaking loop, honestly. Yikes. I really love iterators, but they kind of sucky in some places. Da, da, da. Yeah, just do it like this, dude. Let's not waste more time. So for image and self images, self image views dot push self context. Do I really? Yeah, I do. Image push context create image view image self dot format. Though I could say copied here, I guess. Man, no need. Alright, so it's, of course it's color format. Perfect. Anyway, I wasted too much time with that thing for no reason. Oh my god, I hate this. Okay, cool. So we created the image views and the images. I think that's it. Yeah, probably. Probably. Though we do have another thing that we have to take into account. Maybe not here, I'm not sure. We'll see about that. But for now we could actually use this thing, right? So our Swapchain import, perfect. And let's create the Swapchain. So we're gonna give it the context and the window, make new public. And then we gotta make sure to resize the Swapchain first. So we could recreate it for the first time. And make Swapchain mutable, sure. Make resize public, sure. So we gotta make sure after we create it, we resize it. So we could create it for initially, basically. And then we need a resize thing. PubFN resize, right? And of course we're gonna get that from. Okay, so we have to bubble that down, I think, or not. No, not really. Yeah. So now I need to make this into an actual match statement. Oops. What I did, I have no clue, man. Cancel. And there you go. Okay, cool. Let's actually do this and let's match on the event. Perfect. And now what we're gonna do is window event resized. There you go. So if let some render is equal to self.renders get mutable by the window ID, because this would be a resize for any window, then we're gonna go ahead and we're gonna fetch the render of that window and then we're gonna resize it. Very simple. It does give me the size, but no need. I already have the window. I could just get the size myself. Unless there is something else I don't know. And that's basically it, I think. Is it really? That's it? I guess there's one way to find out. Am I? Yeah, there is validation on, and so far there's no errors, but ooh. create info image extent. Nah, this is just false positives, at least for this one. Yeah, this whole thing is a false positive. So basically there's a race condition in the window, and so I can actually ignore this by, I think, hold on, let me see. This is just a false positive. But apparently there's no other errors, so I guess it's probably correct. But I guess we'll find out later on more. But here, let's see one thing. One thing. Max duplicated messages. Mute message VUIDs. Okay, so I need to copy the VUID. Where is it? Which is the VUID? I think this is the one. Maybe up to here, I think. So just copy this, I believe. Then I could mute that, I think. Why it's called 0? What? Hold on, let me actually copy it and paste it here and see what I'm gonna get. Maybe just that. I don't know. I mean, let's try it. I don't know why I'm going crazy right now. Okay, let's go ahead to here. Let's do this and let's restart and see if we still get these errors. Yeah, we still get these errors. Actually, it's this VUID though. What the heck? Is it the same? I don't know. Either way, let's actually copy this one instead. Let's stop this. Let's remove this. And let's do this. Okay, so right now it actually shows up, which is great. Now let's try to run it again. And there you go. We no longer get that false positive anymore, which is great. The only problem though is, boom. I mean, I expected it to crash, but apparently it didn't, which is interesting. But there we go, we do have a problem. Is invalid. Create info image info is extent is invalid. Now there's two ways we could fix this. We could make sure that the width and height is not 0, or we could just make sure that the windows never are 0. So how we could do that is by too simply, but you know, I think it's probably better to do in the Swapchain. So let's see. Okay, so we're gonna check. There you go. If extent.width is equal to 0 or extent.height 0, we're gonna ignore the resize. So we're not gonna recreate the Swapchain. And that should do the trick, I think. There you go. Perfect. No errors. Great. Lovely. Let's actually implement the drop now. Yeah. So drain image views and destroy the image views, and then finally destroy the Swapchain. Perfect. Let's make sure that that also works perfectly. And we should be done with the Swapchain, I feel like. We could get to the actual rendering. Yep, seems about right to me. No. All types of object created using is supposed to be destroyed prior. Oh, it didn't destroy the surface though. I see now why. So why you didn't do that, dude? Come on. Well, not the context itself. The surface extension, destroy surface. Perfect. Now we're not getting any errors anymore. Great, great, great. So good. Okay, cool. Now we're gonna actually need to create a pipeline and all that crap. And I'm not sure where to even start with that. Okay. So here's our renderer. Apparently, there's Swapchain, context, resize, blah blah blah. Just thinking on how I'm gonna go with this. Yeah, for now, I'm not sure what the abstractions that I'm gonna make for it. Right now, I'm not gonna bother. I'm just gonna do it here in the renderer itself. Okay, so we're gonna start by creating some shaders, and let's just go to the Vulkan tutorial and steal some shaders there. Steal it forcefully, of course. Graphics pipeline basics. Well, next. Shader modules, blah, 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 blah. Okay. There you go. I'm just going to steal this shader for a second. Right? I'm just going to borrow it. You know? Where I'm going to put it? Let's see. Here, let's make a directory, I guess, called, I don't know, res. And, well, we'll see about that anyways. Let's call it shaders. And new file. And we're gonna call this vert, well, shader.vert, yeah. Gonna add it, gonna paste this guy here, and I've actually installed a plugin here in JetBrains IDE. This is why the GLSL file here is also highlighted for me and stuff. So yeah, and in fact it's probably 460 is the last one. And other than that, or you know what, just keep it as 450 for now. I can change it later. File shader.frag. So this is the fragment shader. We're gonna take this, steal it, and put it here. And then we have to actually use GLSLC, which comes with the Vulkan SDK. So if you haven't installed the Vulkan SDK yet, you have to install it to do this. Of course, if it's in the path. If it's not in the path, then you have to look for the Vulkan SDK. Where is it? And then use that. Anyways, so GLSLC res, well, src slash res slash shaders slash shader.frag and dot slash src slash res slash shaders slash shader, well, what I'm doing, no, dash o, right? Res shaders slash frag dot, what is it called? SPV, so SPV, right? Cool. And I'm gonna do the same thing with the vertex. So this basically takes that source code fragment and vertex source code. Oopsies. That shader source code and turns it into binary SPV bytecode. Too simply. There you go. As you can see, we got avert SPV and frag SPV. These are the ones that are needed by our application. Okay, cool. Now we're gonna go to the context. Rendering context, and we're gonna make a new function called create shader. pubfn create shader module, yeah, and there you go. So you're gonna get the code. Well, the code, we would get it as U8 really, right? And then we have to realize how we could actually do this. So in Ash, there is a helper function in util. So it's called read SPV. And you basically have to give it a cursor code, I think. So basically let code is equal to I think it was our cursor new code, probably. I'm not sure why they need that cursor and stuff, but that's how it's done. And that would give you back a vec u32. Can I actually just do this? I don't think. Actually, yeah, I can, apparently. No? Doesn't seem like it. Let's just say let code, and let's just shadow the variable. Don't need the old one, I think. And let's just convert that vector to a slice by doing this, I guess. Yeah, so we just make that vector into a slice. Like, and there you go. Other than code, we also need a name, I think, for the entry point. Well, actually not here. Yeah, somewhere else. So yeah, that's all we need to create a shader module, really. Perfect. So let's actually use it now. Render and fragment shader. Well, let's start by the vertex shader is equal to context create shader module include bytes shader.vert.spv. Oh, so it's actually relative to the renderer apparently, right? Well, that's interesting. Okay, then fine. Let's just get this here from here for now and put it into later on. This is going to be dynamic, not static probably, but for now I don't care. Well, actually I do care. Should I do a dynamic already? Yeah, I don't want to freaking recompile the whole thing whenever I change the freaking shader, man. That's gonna suck so bad. Yeah. Okay, cool. So let's do that, I guess. Then pretty much. So we probably want the rest folder here actually. Outside the source folder. And after that, what we could do, And in fact, these source code things, let's put them somewhere else. Like let's maybe have a development resources basically. So like dev res, because this res is kind of like the thing that would get shipped with the engine, right? And we don't actually need the source code. So the source code could go to here, right? So let's call that shaders 2. And then we're going to put the source code here, apparently. So we're just going to need the SPVs, pretty much. I actually was successful before to actually link these SPVs together and to use them in one module before. But it was a lot of messing around. Nah, let's not do that right now. Okay, cool. Though I may try it in the future when we have at least triangle or something, but whatever. So we have that now, cool. So here I'm gonna basically maybe give it the path actually for now. So you're gonna say shader dot, well, frag.spv, why not? Let's just go that way. Let's actually call it even Lloyd shader module, really. In fact, Lloyd shader module, frag.spv, and fragment shader, Lloyd shader module, vert.spv. Honestly, that's not really the job of the context. Let's leave it as more like as reusable as possible, maybe. Let's just have this as a helper function, honestly, I think. And yeah, and we're just gonna say, so we're gonna have the context, yeah. My bad. Let's just say self. Oopsies, like this, yeah. And let's actually put this here. And here we're going to say self.context dot create shader module, and then we could give it the code here. A necessary and safe block. So path, let's actually make a constant path. I think shaders directory. There you go. Pretty much cool. Well, not context, self. Oh, shit. Bruh. Okay, I see. I see the problem. We don't have the renderer yet. But that's why we have actually created the context just for this. So let's just put this somewhere around here. Let's remove this guy. There you go. Expected rendering context, yeah. So self dot, well, not self, context, too simply, as ref, I think. There you go. Same thing with the fragment shader, and finally perfect. So we got the vertex and fragment shader. And would this actually work? Good question. Now I'm expecting this to say res slash shader slash, right? Though the problem, yeah, I think there was a problem, or maybe it goes from src, maybe, I don't know. Let's see. Cannot find the file specified. Or maybe it's just the, yeah, it's probably just the working directory, in fact, maybe. What? Res slash shaders. Oh, okay. Remove that and remove that. Alright, cool. We're loading the shader modules. Perfect. And now, after that, after we create the pipeline, so the pipeline is going to be very freaking interesting. It's huge. Well, actually, I need to create the pipeline layout first, yeah. No. Builder. Not anymore. This is what, like, we would change this later on when we're gonna need some other stuff. Right now it would be just empty, just a default pipeline layout. Now, after creating the pipeline, we also want to destroy the shader modules. Whoops. Let's put them here. And so between, like, before we actually destroy them, we want to use them in the pipelines. So create graphics pipeline. So context is ref, Swapchain extent, also Swapchain format, because we're using dynamic rendering. So the actual pipeline needs the format, not the render pass. So we have a vertex shader and a fragment shader, and we have a pipeline layout. Perfect. Yeah, let's try to implement this now then. Actually, this should be in the context, really, yeah. True. well, not self context. So create graphics pipeline. So this is gonna be a lot of crazy stuff. Let's see what the AI would do. Swapchain extent and format. Not really Swapchain, but whatever. Let's see what it's gonna say here. Oh boy. Come on. Okay, let's see what we have here. What it generated. Result, of course, we're gonna return back pipeline. Yep. And let's see what we got here. So shader stages. I mean, can't I just say main as? Maybe not. Anyways, can I just do this like entry point? For now, we're just gonna hard code the entry point, really. Though I should probably not do it like this. There you go. Place with that. Just say entry point. Method build not found in the current scope for type. Man, the AI still haven't learned that it's not build anymore. Okay. Vertex input info for now, it's empty. Input assembly triangle list. Whatever. Viewport doesn't matter. Scissor. Okay. Rasterizer. For now, for the call flags, I'm just gonna say none. I guess RGBA. Okay. I see, just say in wrap for now. Or we could say map error. Yeah. So this is basically the error type here is that it gives you the error, but it also gives you the pipelines that are created successfully. Somehow. But I don't care, I'm just gonna get the first error and return it. And yeah. Into editor dot next dot in wrap and okay pipeline. Okay, let's see if this actually works. Temporary value dropped. Can I remove that? Like this. Honestly, I freaking hate this way of doing it. You know, here's how I'm gonna do it. So go on and directly say self dodge device dot create pipeline, graphics pipelines, and then we're gonna say in wrap for now, and into iter dot next dot in wrap. And with that, we're gonna get a vacate pipeline. Then we're gonna say okay, okay. There you go. Now this takes 3 arguments. What are them? Pipeline cache first, and for now we're just gonna stay with pipeline cache none for now. Null. And the third argument is just none for allocation callbacks, and graphics pipeline create info, and of course all of that. That's basically how it should go. Now generate all that stuff for me, please. Oops. Okay. I think I could just say RGBA, right? Is that it? Yeah, it is. Cool. What else? For now, call mode none. Seems about right for me now. And since it's null, there's no need to actually pass it. And since it's 0, there's also no need to pass it. Base pipeline index. I don't know about that. I don't think we need to pass anything there. And in fact, multi-sample state. Okay. So now we're gonna need that dynamic rendering thing. And how you do it is, I think you just push next, right? No, not that. And mutable vacate pipeline dynamic. No. I don't remember what it's called though. So let's check some intranet stuff. Let's look for dynamic rendering Vulkan. There was like an interesting page. Yeah, this one. And it goes through how to actually do some stuff. Doesn't cover a lot, but it covers, I think, enough. Yeah, pipeline creation, there you go. And what is it called? VK pipeline rendering create info cache R, okay. the freak? My IDE is going crazy. Is the stream fine, by the way? Automatically. Yes. Okay. Graphics, well, actually pipeline rendering create info. There you go. Default dot. Okay, so here, instead of having a render pass, you actually give it the stuff that you need here. So you give it how much color attachments you're gonna have. In my case, I think only one. What the heck is going on? Oh yeah, well, let's just use color attachment formats, and then it would assume what the count is from the array. Well, not assume, but like imply or infer, yeah. And here we're just gonna say Swapchain format, basically. I mean, it doesn't have to be the Swapchain, it can be any format of whichever image, honestly, but yeah. Other than that, is there anything else? Attachment. We're gonna need the depth attachment format later on, but that's not the case now. And yeah, I guess that's pretty much it, really. No need for a freaking render pass. Yeah. And this one, we could just call it, so shift 6, extend, shift 6, format. Or image extend image format. Okay. There you go. Okay, cool. I mean, we could include the pipeline cache here. Why not? We could pass it here. But the most important ones are vertex and fragment shader, the image extend, the image format, pipeline layout, then the pipeline cache. Cool. Alright, so I think that's it. We're gonna find out with the errors. If there's anything missing, the errors would tell us. So yeah. The pipeline cache right now, we're just gonna say AK or default basically, which is gonna be basically null handle. Yeah. Yeah, let's actually see what's gonna happen now, if this would work or not. Apparently, and let's actually implement drop. True. But before that, we need to, okay, hold on. Let's do like this. And we're gonna include the pipeline layout. Well, after that. and the pipeline itself. And there you go. Add the missing fields, and somehow it doesn't like, oh yeah, makes sense. Let's pipeline, add the missing fields, and finally let's implement drop here. For the renderer, we're gonna destroy the pipeline, then we're gonna destroy the pipeline layout. And yeah, that's it. Let's see if there's anything missing. The Vulkan configurator would actually tell us. And so far there's no errors, which is good news. Perfect. There you go. By the way, these could be defaults too, why not? What else? For these ones, let's see. So this one's not needed. The default is enough. Triangle list, probably the default is enough here too. What else? What about the dynamic state? Is it okay? The dynamic state. I don't think we included the dynamic state. Yeah, not. So let's do that. There you go. So the viewport and scissor would be dynamic. And since they're dynamic, I don't think right now we're going to need the viewport and the scissors. So the viewport state anymore. But let me just make sure that this actually works, first of all. And no, it doesn't. Something is wrong. Oh no, the triangle list topology thing is actually needed. It's not the default apparently, yeah. So where was that again? Probably here. Yeah, there you go. Let's set it to triangle list because it's not the default apparently. Yeah. Okay, cool. What is the other thing that I wanted? Yeah, if I remove this viewport state, would it be okay? No, it's not. Although the thing is dynamic, but it's not okay. Okay. All right. Though, why the heck it's only giving the width here? That's strange. Width and height and max depth. So yeah, right now I think we're good. We have a pipeline, which is great. Now we actually gonna go into the rendering, the actual rendering, I think. Is it? Yeah. Well, we do need some objects first. Yeah. Some other objects. Okay, cool. But so far we're actually doing a pretty good job. Okay. Let's go to the renderer. And so we're gonna have we're gonna need a command pool and command pool. Okay, let's go ahead and do this, man. So command pool, and we're gonna need command buffers. Though for those ones, we're not gonna put them here. I'm gonna have a struct frame, right? Because I'm gonna have in-flight frames, right? And basically for the frame, we're gonna have a command buffer for every frame. We're gonna have an image available semaphore and render finished semaphore and in-flight fence. And that's it, okay? And then we're gonna have frames. Vec frame and then frame index, which is gonna be usize. And then we're gonna have a constant, well, it doesn't really have to be a constant though. Okay. So let's actually create a command pool. Well, there you go. I mean, come on. Key families. Oh, graphics. Yeah, graphics. And what else? Oh, by the way, hold on, can I go to Swapchain real quick? Just want to make sure one little thing. Exclusive. Yeah, I don't think it's actually that important. I mean, yeah, since it's exclusive, that's only needed if you're gonna share. Anyway, let's not worry about that now. So right now we created the command pool. Next up, we're gonna create the frames. So there you go. So basically, swapchain.images.length. Fine, make images public, whatever. Map that. Actually, no. No, not gonna do it this way. Here's the thing. Let's first of all allocate all the command buffers that we want in one, because this, like, basically it allocate multiple ones, right? And then we're gonna go ahead and create frames. There you go. So we're gonna say command buffers into iterator, then we're gonna map the command buffer, then create semaphore for it, create a fence in signaled state. I hate this. I hate these callbacks, man. So yeah. Let's just say let frames is equal to a vector with capacity swapchain images dot length. Right? Yeah. Or actually, hold on a second. Not really. No. Command buffers dot len. Yeah. And now we're gonna do a regular roll loop, and then create semaphore, create fence, then frames push. Let's make frames mutable, and let's add the missing fields. The frame index would be 0 at first, yeah. And that's it for the initialization, I think. Yeah, probably. And then right now we're actually gonna have a public fn render. Now for that, before we do that, actually, let's go to the swap chain, and we're gonna implement some functions there. Where's my Swapchain? Okay, so we're gonna have acquire next image, correct, perfect. Expected, wiki definition, semaphore. So what we call the semaphore, image available semaphore. Okay, so we're gonna have image available semaphore. It's gonna be a vacay semaphore, and this would go here. The fence, I don't think we need the fence here. So what we're gonna do is vacay fence null, I think, and actually here we're only gonna give a user 2, really, but this would give us two things. It would give us the image index, and is it suboptimal? If I remember. There you go. Now if it's suboptimal, then we're not gonna resize, but we're gonna mark it as dirty. Dirty jail, right? So mark as dirty, or too simply, is dirty is equal to true, pretty much, right? So if it's suboptimal, basically suboptimal means that it's not the best image that you're gonna like the Swapchain is not completely compatible with the window, but you can still go ahead and do the job. It's just not gonna be the best job ever. So what we're gonna do then, we're just gonna continue with this frame until we're done with it, and for the next frame we're gonna make sure to recreate the Swapchain before we actually start the rendering. That's basically it. Now let's add this field. It's gonna be, of course, Boolean, and okay, it's dirty false. Well, actually, at the start, it's going to be true. It's dirty. Make self-mutable, sure. And okay, image index. Yeah, seems about right to me. Let's try it. So where were we using it now? Where's the render function? Have we not created it yet? Oh yeah, we have not. Though we also need another function called present, yeah. Change return type of method present to vacay result bool. Alright. So self context swapchain extension dot q present self dot context dot present q. Well, queues dot self dot context dot present q. Well, queue families. Yeah, pretty much. I do need to check if the present queue is the same as the, or do I? I'm not sure, we'll see. Anyways, wait semaphores. We're gonna wait on the render finish semaphore, and image index. Cool. And what this supposed to actually do? I mean, result, nothing really. And if result is error, success return of the suboptimal for the surface. Ooh. So this is basically is suboptimal. Cool. But still we have a vacant result there. Now, if it's dirty, what the heck is going on here now? Self is, oh, I see. So self is dirty, then self is dirty equals false, and then self resize. I wasn't planning to do the resize in here, but okay. Else if is suboptimal, then self is dirty true. Now, honestly, no, let's not do that here. Just say if is suboptimal, then self is dirty equal true. Pretty much, I think. Yeah. And then just say okay. And there you go. Yeah. Seems about correct. True, true, true. Alright, now let's actually create a new function called render. Render. And let's see what we got. So here we're getting the current frame. So the in-flight frame, basically. Hold on. Oh, well. It's not necessarily the Swapchain images length. No. Let's just call this in-flight. In-flight frames count, right? That's basically what it is. Let in-flight frames count is equal to, let's just say 1 for now. It's kind of like we don't actually have any in-flight frames, right? Okay, what are we gonna do now? Let's actually store this as a field, fine. Do this. Whoops. What? Oopsies, no, that's not what I meant. I found U32, oh, okay. Actually, no, say as U32 here, and there you go, cool. Now what's next? So, expected results but found units. Makes sense. Let's just say okay here. And what's up? make renders. Okay, cool. So now we got the image index. Self.frame index. Yeah, cool. But before we actually try to acquire the next image, actually, bruh, let's go to this tutorial, okay? Because at this point, I'm already, my brain starting to sleep. There you go. Let's go to frames in flight, yeah. Okay, so we wait for fences and reset fences. Okay, let's go ahead and do this. So self.context.device.reset command buffer. Well, that's not the first thing that we want. Wait for fences, reset fences, and then reset the command buffer too. And oh boy, I'm not sure what the heck happened to the IDE again. What? Oh. There you go. So reset command buffer. And now we acquire the next image in the Swapchain. Let wait semaphores equal frame available semaphores. No. Now we're just gonna start the command buffer. So how are we gonna do it? Yeah, let's go ahead and do this. Device begin command buffer. Cool. Okay, so we don't have a render pass. The first thing that we want to do when it comes to dynamic rendering is we want to transition the layout of the image. Now, this is something that would require a good helper function, honestly. And let's actually go ahead and do this. Let's go to the context. Let's first of all create a little helper struct. I'm gonna call this, I'm not sure exactly, but let's call this image layout state maybe, or something like that. Right, so, and it would basically have access mask, layout, and a stage mask. That's it, I think, yeah. That's the image layout state. That's just a made up thing that I made. Though there's nothing called like that. But you're gonna see what I'm trying to do here. So basically we're gonna have transition image layout function. Should use pipeline barriers, of course. And what the heck? No, don't create a command pool, bro. What the heck? No, 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 no. So first of all, please give me a command buffer that you're talking about. And second of all, give me the image, yeah. And you're gonna give me the old state, which is image layout state, and then the new state, which is the image layout state. Let's see if the AI can do this. And all sense also include the key family index, why not? So redo this, please. Or too simply, what I'm gonna do, I'll remove this and open this up. And there you go. There you go. There's also the aspects mask though. So for that one, so we got the command buffer, the image, old state, the new state, and why not the aspect, I guess. Because it could be like something else other than color, like depth, maybe. Of course, I'm making a lot of assumptions here, but that's just to make things easy for now. Okay, so that's cool. That's just my little idea here to actually make a little struct like this, to stuff like that. But yeah, pretty much. Now let's go back here. And after beginning the command buffer, well, let's just quickly end the command buffer first of all. Okay, and in between, right now we're gonna transition the image layout from undefined to color attachment. Okay, and well, okay, hold on. So the rendering context here, is it public? Yeah, it is. Cool. So basically, I think image layout state. No, dude. No. Okay. Also the Q family, yeah. I'm gonna ignore it right now. And the new state, which is gonna be color attachment optimal right, color attachment output. So basically we're transitioning the image from undefined to be able to like color attachment, so we can actually render to it. So takes 5 arguments, yeah. And I think the last one was probably aspect mask. Color, of course. Is there anything else? Doesn't seem like it. And what does it return, by the way? Nothing. Cool. Perfect. So now we can actually start our render pass. But before that, let's just transition it back before I forget about it. Okay. So transition image layout to present. Okay. The AI is really helping out here. Cool. So we have image layout. So we're going from this. Well, actually, this should be the same thing. This new state and this old state here, these are the exact same things, right? So let's call this, I guess, renderable state, maybe something like that. I don't know. So yeah. And this is basically it. Now this and this should be the exact same things, right? Derive copy trait. Where is the thing? You have clone and copy, which is okay. So that's cool. So yeah, there you go, dude. There you go. Transition image launch to present. So as you can see here, it's the new state here and the old state here, which is cool. We could also create the other ones too. Like we could say present image state. Oh boy. There you go. Let's undefined image state, and this is what you have here. So you see where I'm going with this? So you're from undefined image state to renderable image state to present image state. Perfect. Now before we transition to the present state, we want to actually begin rendering using dynamic rendering, where we don't have render passes here. So how are we gonna do that? I stop begin CMD begin rendering, yeah. Or I could just fine, just do it directly. Begin rendering. Though actually, yeah, never mind. Let's just go ahead and say begin rendering. But let's actually do in the context, yeah. Oh boy, how much code is that? Craziness. Craziness. Oh my god. Hopefully at least we get a triangle today. Damn. So command buffer, yeah. No, we don't have a render pass. No thanks. We have a render area. And some other stuff, but we'll see about that in a second, dude. So in safe, and here we're gonna say begin rendering. CMD begin rendering. Yeah, there you go. And the command buffer, and Oh my god, the AI really wants me to use a like render pass. It just wants to shoehorn a render pass anywhere. Because not a lot of people use this. Anyways, so the layer count is probably 1. The render area and the color attachments. So for the render area, select 2D. So for the render area, it's gonna be the Swapchain thing, but or actually instead of the render area, let's start with the color attachments first. There's also depth attachment there. Anyways, so color attachments and rendering attachment info. Rendering, oh well, vk rendering attachment, okay, attachment info, default. Okay, so here you give it directly the image view. No stupid indices or whatever, so that's great. So the image view, you're gonna have it here. Or let's just call it just view, why not? Make image view. So view. Whoops. The image layout. Color attachment optimal. I'm not sure why would I have anything different than that. Okay. And what else? Clear value. So clear color. Here where I'm gonna use that palette. So clear color, vk clear color value. Well, actually not that. Let's go with palette as I said. Well, it depends if the thing is actually sRGB or not, though. Let's not overcomplicate things. Just clear color value, please. Thank you. Or we could just assume that it's sRGB. Whatever, let's just do it directly, please. Clear color. Clear color but found. Oh. Expected clear value. Oopsies. It's either clear color value or interesting. You know what, let's just say clear color value, and then here, whoops, vacate clear value default dot color. No, color clear color. I don't know why it keeps on freaking up my thing here. I hate it. There you go. The resolve image view, no need. So the image layout we already have set it that one. the Lloyd OP clear dot store OP store. Oh man. Okay, dot resolve image view, resolve mode. That's for multi-sampling. We don't need that now. And yeah, I think that's probably it for this one. Well, color attachments, what else there is? Color layer count. And finally, at least for now, render area. I'm ignoring the depth attachment completely right now. And for the render area, we're just gonna give it a render area. Perfect. That's probably all we need for now. There's a lot of assumptions right there for now. That should be okay. Cool. So let's go ahead to renderer and command begin render pass. Well, no. Self.context of begin rendering. Whoops. Whoops, whoops, whoops. It's not helping. Frame.command buffer and then self, well, yeah, I need to get the Swapchain image view, dude. And then the clear color. So clear color, well, vacate clear color value. Float 32. Whoops. There you go, I guess. No, apparently not. So no. Let's just say this. Float 32. There you go. And direct is that. Though instead of this, we could just use the builder pattern, say default.extent, Swapchain extent. Here we could just for now say Swapchain. Dot views. What? Is it called maybe image views? I don't get it. Okay. Though I'm just gonna say that this should be called views. And there you go. Views self.frame index. Is the stream still fine? It's already 5 hours. Crazy. Alright. 5 hours is like nothing for me when it comes to programming. And anyways. So this is the clear color. Let's say red. Okay. What's next? Yeah, let's bind the pipeline. Let's draw 3 vertices. And then let's end the rendering. For that, we're just gonna say self.device.end cmd. Not render pass. Come on, bro. What the heck is going on with you? The AI really loves the render pass. We don't have it. Sorry. I hate them. And then end the command buffer. Yeah, and that's it. That's it. Now we gotta submit it. Yeah, gonna submit that thing. Reset fences. What are you talking about? No. Let's submit the command buffer now. So qsubmit. Perfect. And present. Hold on. Yeah, that seems about right. I think we're done. Maybe. Why the heck are you enumerating here? Oh, method render never used. So let's use it. Where are we gonna use it? Okay. Engine. And let's go. About no. Ooh, scale factor changed. Sure, I guess. Let's resize that there too. I don't care about that one. And what else? I think request redraw. Go on. No. There you go. Next. Okay, so next up we're gonna need the about to wait. Redraw requests. So we're gonna find that. Yeah, we're gonna find that here. Generate, implement methods, about to wait, okay. And here we're gonna I don't think that's, no. Let's just say self the engine. Well, if let some engine, then engine.request redraw. Too simply. Now in engine, I'm gonna say pubfn request redraw. And we're gonna request redraw for all the windows that we have, basically. And that should do the trick. I think that's basically it. Oh my. I mean, we're kind of getting something, but it's strange. What the heck is that? Oh, viewport. I see. Da da da. Okay, so bind pipeline. No. um, viewport. Scissor. Maybe that's all we needed. I mean, we're getting yeah, we're getting the triangle, but something is very strange around here. Not entirely sure what's causing that. Oh. So like when you request redraw maybe a window, it's kind of like it stops the other windows from requesting redraw. Yikes. And when there's two windows for whichever reason, it's kind of strange. Okay, well, let's first of all clean up some stuff before we go forward with this. Or, you know what, let's go to the engine, I think, right? No, the app, yeah. Let's not create a secondary window. Let's just have one window and see. Good, but it still have that strange, you know. Some strange flickering. Why? Interesting. Well, we're getting the triangle. But something is strange with the flickering. And one window's request redraw blocks the request redraw for the other windows, apparently. I don't think that's probably the limitation of Win itself, maybe. But I don't know. Alright, so I need to figure out though the flickering, why that's the case. Okay, I'm gonna take a little 5 minutes break and then we're gonna be back. Okay, back. Let's go. The mic is on, camera is on, perfect. So, let's make sure to destroy this stuff first before I forget. Destroy command pool, yeah. What else? Yeah, drain the frames. For each frame, context. Destroy semaphore, destroy fence, free command buffers. Well, free command buffer should be once, though. Oh, actually... I see. So no, I can't do that. Let's just do it that way then, fine. Or... whatever, dude. Okay, is there anything else? Doesn't seem like it. That's cool. Anything else? I don't think so. Either way, so that flickering, it could be the blend constants. Could be. Let's see. So the rendering context, the pipeline. Okay, so I could have something crazy going on there. Okay. I don't know. Let's actually check what they did here. Because I can't think of something else that could do such a problem. Fixed functions. Blend enable false and color right mask all of them. That's it. So no, it's not a problem there. I think, yeah, it's not a problem there at all. So let's just get it back as it was before GBA. I mean, we do have only one window now, so yikes. It could be this something in the Swapchain creation too, dude. Destroy fence. Oh yeah, well, before we destroy the render, by the way, we have to wait. Idle. Device wait idle. Let's try this out. Oh, what the heck? Now it somehow works. What the freak? The thing is, this is not what I meant to actually where to put this thing in. Like, I didn't mean to put it here. I meant to put it in here. fix some problems there. So it could be a problem with synchronization, since that kind of fixed it there. Could be a problem in synchronization. Oh, well, but I don't think it matters here because we only have one frame right now. But it still matters. So there you go. But yeah, I don't think it would matter right now because we only have one frame, in-flight frame. So yeah, that's not the problem. But it is a problem. So yeah. Okay, I'm gonna be back in a second. Okay, back. So I do have some mic is on, camera's on, great. Okay, so I do have some things that I'd like to check. First thing that I'd like to check is to make sure that the event loop is in the right mode. Control flow pull. Hopefully this is the problem. No, it's not. But why it's perfectly fine when I actually resize the window? Yikes. I mean, we could fire up our debugger, so we could use render doc right now. So apparently when you're using that, you should not have this on. Okay. Now let me copy the path there. Target debug build. Well, not that. Code Chaco engine, and let's copy path, absolute path, and let's go to render doc, paste in the executable path, and let's launch this thing. And whoops, what happened? What in the world? Oh, I see. So Code Chaco engine should be the working directory. I think that should work. What the heck? I'm gonna copy this working directory. There you go. Cool. Okay, so why this stuff happens? Let's capture a frame using PRT screen. And let's see what the heck. So as you can see, we are getting a good, like the image gets rendered correctly. It's just that I see some flickering for whichever reason. Maybe the Swapchain setup could be somehow wrong. Whoa, we're still live. Yeah. So what's happening here? I'm queue submitting. Like vk begin command buffer. Then vk-cmd begin rendering, draw, end rendering, end command buffer, and queue present. It's probably something to deal with the Swapchain OS, because there you go, the image gets rendered correctly, nothing crazy there. So it's probably something to do with the Swapchain or the synchronization. What if I change the present mode to mailbox, let's say? I mean, I'm just getting some weird other flickering, but it's not the same flicker. How? I don't know. Oh, by the way. No, well. I'm not using, by the way, the is dirty thing. So maybe it's suboptimal because I'm not actually trying to. Ooh, okay. Yeah, let's try that. How are we gonna do it? Let's see, render. So I guess maybe after we wait for the fences, let's see if self.swapchain is dirty, then resize the swapchain. So that was the problem. I wasn't recreating the swap chain when it was suboptimal, I think. That was the problem. So I was just checking the sdirty flag and that's it. But there you go. We got the freaking triangle. Let's change the red, the clear color from red to black or something like that. Let's say 0.1, maybe 0.1. You know, not completely black, but black. Well, that's sRGB, I forgot. I don't know, let's say 0.01, I guess. Oops. Yeah, not bad. As you can see, it works. We got the crazy triangle. And it's actually very smooth since we're handling the request redraw correctly. Very freaking smooth. And this is just a debug build, by the way. Anyways. Yeah, now let's try to add in the secondary window that we have removed before. Let's see. Let's go. We got like multiple window rendering with Vulkan and Rust. Oh my god. Okay. Man, that's perfect. Just perfect. Oops. There you go. That's the crash that I was talking about. Error out of date KHR. In here. Out of date KHR engine.window event. Let's see. How are we gonna handle that? Well, I guess let's go to Swapchain. And resize. We're already checking that. So yeah, where we're getting the out of date, I don't get it. Bro. I guess I should just mark it as dirty and then recreate in the next frame, I think. Like, for real. Yeah, pretty much. When you get an outdated error for a key presenting, you need to create the swap chain to match the new conditions. I know, but like when exactly? This involves. Should I do it immediately? Okay. Let's see what we could do. So if we have error out date error, then we're gonna map it. Well, actually not map it. No. Hold on, dude. Hold on. So instead of doing this, we're gonna match on this. So if it's suboptimal, then well, suboptimal. Error out of date, self is dirty true. We're gonna say false. Okay, and then return. I mean, why not just say true and then it would set the is dirty for you. I think. Okay, let's try. Perfect. Okay, it works. Lovely. No longer crashes on that. Great. Alright, so yeah, we're pretty much done, I guess, with the first live stream. How much time it took? 5 hours and a half. Man, it's not just the freaking Vulkan renderer, where like it's the whole structure with multiple windows rendering. Oh boy, that's cool. That's cool. Yeah. All right. Let me commit all this stuff. Cargo log for sure. Cargo channel, main RS, virtual SPV, frag SPV, and of course all the changes. Get ignore, yeah. And here we're gonna say slash dot idea. And yeah. The triangle. Commit. Commit contains problems. Rename is never used because I don't care about it. Amend the commit. There you go. Okay, so is there any questions before we end the stream? I think we've done pretty good job today. Let's by the way try to open it in RenderDoc again and see if there's anything. By the way, hold on, I didn't try one thing. Hold on. We're still not doing in-flight frames, dude. I mean, yeah, it's implemented, but I only set it to be 1. So like, hold on. In-flight frames count. Let's say 2 frames. Just to make sure. Oh boy, what the heck is going on here? Freaking flicker it again. What the heck? Why? But you know, at least one framework. But like, why 2 frames? What was the problem anyway? Yeah, it's dirty thing. I see. But hey, I'm too tired for that now. Fix flickering when greater than 1. We're gonna try to fix it in the next stream. For now, I'm just too tired. So yeah, thank you Theo Paris channel, OG Gearing, Loop Preliminary, Robert, Hello World, One True Blue for coming to the stream. Thank you all. And I guess see you in the next one. Like, I'm just thinking, is there anything? Yeah, by the way, I'm gonna actually publish this and I'm gonna send the link in like, I'm gonna publish it to GitHub. I'm gonna send the link in the, what is it, in my Discord server. Okay, you can join my Discord server in the description below. So that was it, guys, for the stream, and see ya in the next one, maybe tomorrow.